The universe is expanding, and it isn't pushing into anything. Every galaxy is racing away, not from a centre, but because space itself is stretching, like a map that grows without adding a single new edge. If there is no outside, no empty nothing beyond the cosmos, what could expansion possibly mean, and how can reality get bigger with nowhere to go? Tonight, we put nothing on trial and demand a verdict from the laws that govern reality. If the cosmos has no outer wall, then our language may be the first thing that breaks. What we call expansion is not a headline, it is a measurement, repeated across decades and across sky after sky. It hides in the faint drift of spectral lines, in the cooling afterglow of the early universe, and in the quiet arithmetic of distance. Yet the moment we translate that measurement into a mental picture, intuition reaches for a container. We imagine an arena, a background, a place where space can spread. General relativity refuses that comfort, because in its grammar, space and time are not scenery. They're dynamical, responsive, and counted among the actors, with geometry doing real physical work. When you change the geometry, you change what a distance even is, and the universe can transform without borrowing room. That is the doorway into our paradox. The word into may be the wrong preposition for cosmology. To understand what is truly being claimed, we have to separate motion from metric change, between galaxies travelling through space and the rule that turns coordinates into ruler readings. We will watch how light carries evidence across billions of years, and how that evidence can be misread if we force it into everyday notions of speed. We will face the unsettling fact that some separations grow so fast that no signal can ever bridge them, while local physics remains perfectly lawful. Then the story moves backward, toward an earlier universe that behaves less like an explosion and more like a state of extreme conditions. We will see why a simple hot beginning leaves puzzles stamped into the sky, and why cosmologists proposed a brief, violent growth spurt to explain the smoothness we observe. That proposal is elegant and controversial, and it leads directly to a deeper question about origins. Because nothing is not a single idea. There is empty space, there is the quantum vacuum with its restless structure, and there is the possible absence of space-time itself, where before may not be a meaningful direction. Each meaning points to different physics, different evidence, and different limits on what can be known. And just as the picture begins to settle, the universe delivers another twist. Its expansion is not merely continuing, it is accelerating. That acceleration reshapes the far future of observation, drawing a horizon around what can ever be seen, and forcing us to ask what outside could mean when causality itself sets the boundary. This documentary is an expedition through those boundaries, from data to geometry, from early time conjectures to late time surprises, and from comfortable metaphors to the hard edge of theory. Along the way, we will treat every analogy as a tool, useful, imperfect, and sometimes dangerous, because the universe is under no obligation to fit inside the pictures our brains prefer. If there is a paradox here, it may not be in space at all. It may be in the way we insist on imagining it. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will follow the evidence from Redshift to horizons, from inflation to the quantum vacuum, and into the debate over dark energy. By the end, nothing will look less like emptiness, and more like the deepest question we can ask about existence. A balloon swells under a soft studio light, its rubber skin creaking as it rounds out. Dots on its surface drift apart and the picture feels complete, until a simple question lands with surprising weight. Where is the edge, and what is outside? Raisin bread rises in an oven, the crust browning as heat drives bubbles through dough. Every raisin separates from every other raisin, without a center raisin commanding the motion or issuing orders. Yet the mind still asks what the loaf expands into, as if an unseen container must exist. An infinite grid stretches across the screen, lines sliding away from one another in perfect proportion. No boundary appears, yet every square grows wider, and every diagonal becomes longer. If there is no border, the phrase expanding into something starts to sound wrong, almost like grammar trying to force physics to behave. Cosmic expansion is the claim that space itself grows, not merely the stuff inside it. Not galaxies flying through a static emptiness, but distances increasing because the metric changes with time. That sentence is where intuition breaks, because the change is not a push, but a remapping. Everyday experience trains a specific model, and it is hard to unlearn. Things expand by pushing into pre-existing room, and the room stays the same, like a warehouse that never moves. A gas fills a container, a fireball spreads, and a shockwave races outward through air that was already there. That model smuggles in an outside space, even when we do not notice it. It assumes an edge, a background, and a place for the boundary to move as the object grows. It also assumes expansion is motion through space, not a change of space itself. Cosmology asks us to drop that habit, because the universe is not a balloon inside a bigger room. In general relativity, spacetime is not a stage that sits there waiting for actors to enter. Spacetime is part of the physical system, shaped by energy, momentum, and pressure. Einstein's insight was not just mathematical elegance, but a new kind of causality. Matter and radiation tell spacetime how to curve, and curved spacetime tells matter how to move. When we say the expanding universe, we mean the scale of spatial separation changes with time, everywhere at once. The coordinates can stay put while the proper distance between them grows, like marks on a ruler that slowly spread apart. A galaxy can be at rest in comoving coordinates, yet still become farther away as the scale factor increases. Expansion becomes geometry, not travel, and that distinction matters. The paradox arrives immediately, and it arrives in plain language. If space is all there is, what could it expand into, and where would the new space be located? If there is no external space, what does the word into even mean? The documentary begins with that confusion on purpose, because it is the honest starting point. The phrase into nothing sounds like a contradiction, yet it is close to what the equations suggest. Our task is to separate language from physics. We need to define nothing carefully, because it hides more than one idea. Nothing can mean empty space with no matter. Like a vacuum chamber pumped down until air molecules are rare, nothing can also mean the absence of space itself, which is harder to picture and harder to state. Even the word space is slippery, and our brains treat it like a container by default. In everyday speech it means a room, but in relativity it is a set of relationships between events, distances and durations measured by rulers and clocks. The universe is not an object sitting inside a larger room, because room is part of the universe. This is why the balloon analogy both helps and misleads in the same breath. It shows how every separation can increase without a special center, and how local observers all see others receding. But it tempts us to imagine a higher dimensional outside, and the real universe does not require that outside. The raisin bread picture carries a similar double edge. It correctly removes the idea of a privileged center, since every raisin sees others move away as dough stretches. Yet it still suggests a kitchen, an oven, and surrounding air, backgrounds that cosmology does not automatically grant. We also need to handle the Big Bang with care, because popular images are almost designed to mislead. They show an explosion erupting into darkness, with debris flying outward from a point like shrapnel. That picture is almost guaranteed to create the wrong question, because it bakes in an outside. The Big Bang is not an explosion in space, and it is not a fireball expanding into empty surroundings. It is the early, hot, dense state of an expanding universe, where the scale factor was smaller and conditions were extreme. Space was already there in the model, and it was changing as the contents cooled. Historically, this idea did not appear fully formed in a single moment. In the 1920s, solutions to Einstein's equations by Friedmann and Lemaitre showed that a dynamic universe was mathematically natural. A few years later, Hubble's observations turned that possibility into a measured trend in the sky. If the universe has no edge, the Big Bang had no center, and that is a difficult sentence to make intuitive. Every region was once closer to every other region, and the whole observable cosmos was compressed into a much smaller volume. Expansion then is the unfolding of distances everywhere, not a blast from somewhere. The evidence for this is not philosophical, and it is not a preference for one metaphor over another. It comes from light, spectra, and the way galaxies appear to recede in proportion to distance when averaged over large scales. It comes from the cosmic microwave background, a relic glow from an early era. When we measure redshift, we see wavelengths stretched, and we see the pattern in atomic spectral lines slide toward longer wavelengths. In a laboratory, those lines are fixed by quantum transitions, so their displacement is a clean ruler. The simplest story is that space stretched while the light travelled, lengthening the wave like a drawn-out spring. The farther the galaxy, the more the light has been stretched by cosmic expansion, and the more its spectrum shifts toward red. This is not merely a Doppler effect from motion through space, although nearby galaxies can be described that way. Over cosmological distances, the redshift is tied to the changing scale factor between emission and observation. This leads to the Hubble constant, the number that links distance to recession speed in the nearby universe. It is a measurement of how fast the scale of space changes today, expressed as kilometers per second per megaparsec. It is also a clue to the age and history of expansion, because a faster present rate suggests a shorter timescale if the rate had been constant. But even here, words can trap us, because recession speed is not always a spaceship speed. In an expanding universe, distant galaxies can separate faster than light without violating relativity, because the metric is changing rather than objects racing locally. The statement sounds like another paradox, but it is a reminder to ask what kind of speed we mean. Relativity's speed limit applies to motion through local spacetime, measured in a small region where space looks approximately flat. It does not forbid the growth of the distance between far apart co-moving points when the geometry evolves, so the universe can have superluminal recession at great distances, while every galaxy still measures nearby light behaving normally. So why does any of this matter beyond a clever puzzle that philosophers might enjoy? Because cosmic expansion is tied to universe origins, to the meaning of time, and to the fate of everything we can observe. The expansion rate is a key part of the universe's biography, its past chapters and its possible endings. If expansion slows, gravity may eventually halt it, depending on the total energy content and curvature. If expansion accelerates, the universe may thin out into a colder, darker future, with galaxies slipping beyond one another's horizons. The discovery that expansion is accelerating forces a new ingredient into the story, and it forces us to ask what we missed. That ingredient is often called dark energy, a name that admits ignorance while pointing to an effect. It is a label for whatever makes the expansion speed up, as if space has an energy that pushes on its own geometry. In general relativity, pressure gravitates too, and a sufficiently negative pressure can drive accelerated expansion. This turns the question of nothing into a question about vacuum physics, because the vacuum is the closest thing we have to nothing with measurable consequences. If empty space carries energy density, it can curve space-time even when matter is absent. The paradox becomes sharper. The nothing might be an active source. The stakes are also conceptual, and they reach beyond astronomy into the foundations of physics. If space-time can expand, then space and time are not passive bookkeeping devices. They have dynamics, and those dynamics may have begun in conditions where quantum effects mattered as much as gravity. This is where inflation enters, not as a decorative add-on, but as a proposed early episode of extremely rapid expansion. Inflation is driven by a high-energy field in a particular state, and it was designed to explain why the universe looks so uniform across vast distances. It also explains why space appears so close to geometrically flat, even though curvature could have grown noticeable over time. Inflation also sharpens the into-nothing puzzle, because it shows how quickly geometry can change. If space can expand exponentially, tiny regions can become enormous without needing an external arena or a surrounding medium. The vacuum itself becomes an active player, less like emptiness, more like a physical state with rules. But what is the vacuum really when quantum theory is taken seriously? In quantum field theory, empty space is not truly empty, because fields fluctuate even in their lowest energy configuration. Those fluctuations are not just philosophical noise, they can leave measurable traces, and they can contribute an effective energy density. So nothing might not be nothing, at least not in the everyday sense. It might be a quantum vacuum with properties, energy density and pressure, even when no particles are present. Or it might be the absence of classical matter but not the absence of fields, symmetries, and constraints. Yet we must not jump ahead, because Chapter 1 is about framing the question precisely enough that later answers can be tested. The goal is to replace the image of an expanding object with the idea of an evolving geometry, described by equations that can confront data. Once the language is cleaned up, the paradox becomes a guide rather than a trap. We also need to acknowledge a limit that is easy to forget when visuals show the whole cosmos at once. We can only observe a finite region, bounded by the speed of light and the age of the universe, because information takes time to travel. The observable universe is not the whole universe, even if the whole universe is all that exists. This creates another subtle confusion, because people ask what lies beyond the edge they imagine. Often the edge is just the horizon of what we can see, a boundary set by light travel time and cosmic expansion. Beyond that horizon there may be more space, more galaxies, and the same laws continuing, simply out of reach. If the universe is infinite, it never needed to expand into anything, because there was never an outer boundary to cross. It could have been infinite and still have a changing scale factor, with distances between co-moving points increasing everywhere. Infinity can expand without gaining an outside, a sentence that sounds strange until the geometry is made explicit. If the universe is finite, it still may have no boundary, and this is another place where analogy helps carefully. It could be like the surface of a sphere, finite area with no edge, except in 3 dimensions rather than 2. In that case, asking what is outside may be a category error, like asking what is north of the North Pole. So the core question becomes sharper, and it becomes mathematical rather than poetic. In general relativity, what does it mean to say space expands? And what does the mathematics actually require about curvature and energy? Does the theory imply an outside, or does it only describe internal relations among events? We will follow the evidence step by step because this subject punishes shortcuts. First, we will use Redshift to ground the idea of cosmic expansion in observation, not just in metaphor. Then we will confront spacetime directly through general relativity and the Friedmann equations, where expansion becomes a term in a dynamical balance. From there we will test the early universe story, and we will watch how a hot plasma becomes a transparent cosmos. Inflation will appear as a mechanism that makes expansion behave in unfamiliar ways, and it will connect tiny quantum irregularities to the large-scale structure of galaxies. The quantum vacuum will appear as a candidate for what nothing really means, and why empty can still have consequences. Then we will return to the present, where the expansion rate is measured with multiple methods and compared with unsettling precision. Dark energy will force us to ask why expansion accelerates now, and whether vacuum energy is constant or evolving with time. The fate of the cosmos will hang on that answer, because acceleration changes what remains observable and what becomes forever lost. We will also keep the horizon in view, because it is an honest boundary on knowledge. The observable universe sets a limit on evidence, not necessarily a limit on space, and that difference shapes what questions can be answered with data. When we talk about the whole universe, we must remember how much of it is inferred rather than seen. Finally, we will face the most speculative possibilities that are already hinted at by the mechanisms we have introduced. Some versions of inflation suggest eternal expansion that spawns many regions with different conditions, separated by horizons that never meet. The word multiverse enters, not as fantasy, but as a consequence some models cannot avoid once their mathematics is taken seriously. For now, we stay with the paradox of into nothing, because it is the doorway to clearer thinking. The phrase is a linguistic shortcut that may hide a deeper truth about spacetime and about what we mean by existence. If expansion is the stretching of the map itself, the demand for an outside may be the wrong demand. The mystery is not whether the universe expands, because the light has already answered that. The mystery is what expansion means when space is the thing that changes, and when time is the parameter that tracks that change. To solve it, we start where physics starts, with what the light is telling us. Next, we follow the redshift trail, and let observation force our intuitions to adapt. Chapter 1 left us with a grammar problem that feels like a physics problem, because when the map stretches everywhere, the word into starts to mislead. The phrase sounds directional, as if the universe had an outside, a rim, and a blank beyond it. Yet the claim we are chasing is not poetry, and it is not a preference. It is a statement that can be checked against light, against numbers that do not care what we expect. So we pivot from unease to evidence, because the sky keeps receipts. Cosmic expansion is not a mood or a metaphor. It is a measured pattern in light. The record is written in photons that have crossed millions or billions of years, arriving with their wavelengths altered in a consistent way. When we read that record carefully, the universe refuses to sit still. In the early 20th century, telescopes showed faint swirling patches called spiral nebulae. smeared like pale pinwheels on glass photographic plates. Some were bright enough to sketch by hand, and others were barely more than a ghostly oval. Astronomers argued whether these objects were nearby clouds inside the Milky Way, perhaps forming stars in our own neighbourhood. Others suspected they were island universes, entire galaxies far beyond our own, separated by intergalactic darkness. The dispute was not settled by philosophy, and it was not settled by rhetoric at a podium. It was settled by distance, because distance turns a smudge into a scale. If a spiral nebula was inside the Milky Way, it had to be relatively small and relatively close. If it was far outside, then that same apparent size implied a structure as vast as our entire galaxy. Distance in astronomy is built like a ladder, because no single ruler reaches across the cosmos in one clean step. You cannot stretch a tape measure to Andromeda, and you cannot triangulate a galaxy cluster with the naked eye. Each rung is calibrated by a closer rung, then extended outward with careful overlap and repeated cross-checks. The ladder is powerful, but it is also fragile. One weak rung can tilt the whole construction. The first crucial rung came from Cepheid variable stars, which do not shine steadily like most stars in the night sky. Cepheids brighten and dim with a stable rhythm, swelling and contracting as their outer layers trap and release heat. This pulsation is driven by changes in opacity, especially from ionized helium, which acts like a valve in the star's atmosphere. The physics is intricate, but the outcome is simple. The star keeps time. Their period correlates with their true luminosity, so the pulse becomes a standard candle. A Cepheid that takes longer to brighten and fade is intrinsically brighter than one with a shorter period. That relationship is not a guess, and it is not a curve fit without meaning. It emerges from stellar structure, from how mass, temperature, and pressure balance inside a star. If we know a Cepheid's intrinsic brightness, we compare it to its observed brightness, which is reduced by distance and by whatever dust lies in between. The dimming tells us distance through the inverse square law, because light spreads out as it travels. Double the distance, and the same light is diluted across 4 times the area. The method is simple in principle and brutal in practice, because real starlight is filtered through crowded fields and imperfect instruments. Henrietta Leavitt discovered the period luminosity relation by studying Cepheids in the Magellanic Clouds, where the stars are all roughly at the same distance from Earth. That detail mattered because it let her compare brightness differences as true luminosity differences rather than distance effects. Working at Harvard as a computer, she measured, catalogued, and noticed a pattern that others had missed. Her work turned variable stars into cosmic yardsticks, and it also showed how hidden regularities can unlock enormous scales. Edwin Hubble used Cepheids to measure distances to spiral nebulae, focusing on Andromeda and other prominent targets. Through the telescope, the nebulae were no longer pure smudges, but resolving them into individual stars was still a technical struggle. When the numbers came in, they were too large for a Milky Way interpretation. The nebulae were galaxies, and the universe suddenly became bigger not by imagination but by calculation. That expansion of scale set the stage for a deeper surprise, because once galaxies were recognized as distant systems, their light could be compared across vast baselines. A galaxy's glow is not just brightness, it is information spread across color and wavelength. Spectra became the next tool, and they offered something even more decisive than a distance estimate. They offered a fingerprint of physical law. A spectrum is a barcode of physics, produced when light is dispersed into its component wavelengths. Atoms and molecules absorb and emit at specific wavelengths, leaving dark absorption lines or bright emission lines in a rainbow band. Those lines are fixed by quantum structure, by the allowed energy levels of electrons. Because the rules of quantum mechanics are universal, the same patterns appear in laboratories on Earth and in stars across the sky. When astronomers split galaxy light into spectra, they found a consistent shift that was difficult to ignore. The familiar lines appeared displaced toward longer wavelengths, sliding toward the red end of the spectrum. The shift was called redshift, because longer wavelengths look redder to human eyes. On a screen, the effect can be shown as a set of crisp lines. Then the same set, nudged rightward as if the universe itself had tugged on them. Redshift is easy to describe, but easy to misinterpret, because our everyday intuition reaches for motion. In ordinary life, a wavelength shift usually means motion through space. A siren changes pitch as it passes, compressing sound waves as it approaches and stretching them as it recedes. Light can do a similar trick, and astronomers had already used that trick to measure stellar motions. That is the Doppler effect, and it is real in astronomy, especially when objects are relatively nearby. Nearby stars orbit the Milky Way's centre, and galaxies in our local neighbourhood drift under mutual gravity. Their spectra shift accordingly, and for small distances Doppler language works well. In that regime, the shift maps cleanly onto a velocity, like a radar gun for the cosmos. But cosmology adds another mechanism that looks similar in data, and it becomes dominant across the larger scales. Over long travel times, light can be stretched because space itself stretches. The wave is not only emitted and received, it is carried by a changing geometry. While the photon moves, the metric that defines distance changes, and the wavelength is dragged along with that change. Cosmological redshift is not mainly about galaxies racing through a static void, as if they were shrapnel from a central blast. It's about the scale factor changing while the photon is in flight. The wavelength grows in proportion to the universe's expansion, so a factor of 2 increase in the scale factor means the light's wavelength doubles. In plain terms, the universe enlarges the ruler used to measure the wave. This distinction matters because it changes what we mean by recession speed, especially when we talk about very distant galaxies. Doppler speed is a local velocity through space, measured in a local inertial frame. Cosmological recession is the growth of distance between co-moving points, a distance defined by the evolving geometry. The same word, speed, can describe both, but the underlying meaning is not the same. Co-moving means a galaxy can sit still in the expanding coordinate grid, like a dot printed on a balloon as the balloon inflates. It keeps roughly the same cosmic address while the ruler between addresses lengthens. The motion is in the metric, not in a rocket engine. Gravity still binds local systems, so galaxies do not expand internally, and neither do solar systems or atoms. Hubble combined distances and redshifts and found a striking trend that looked almost too simple. On average, the farther the galaxy, the larger the redshift, and the data points formed a line. Distance and recession lined up with near-linear simplicity, at least when the sample was limited to galaxies not dominated by local peculiar motions. In a universe full of complexity, the large-scale pattern was clean. This became Hubble's law, and it is one of the most important empirical relations in cosmology. Recession speed is proportional to distance, at least for the nearby universe where the relation is cleanest. The proportionality constant is the Hubble constant, often written as h0, where the 0 denotes the present epoch. In practice, the speed is inferred from redshift, and the distance is inferred from the ladder. The law is often written as v equals h0 times d, and it looks like a speed limit story, yet it is really a scaling story, a statement about how the cosmic ruler changes with time. Double the distance and you roughly double the recession, because the same fractional expansion applies everywhere. The simplicity is not accidental, it is the signature of a uniform expansion. The implication is not that we sit at the centre of an explosion, with galaxies flying away from a privileged point. Every observer in a uniform expanding universe sees the same pattern because the expansion is built into the geometry. The proportionality emerges from homogeneity, not from privilege. If you lived in another galaxy, you would draw a similar line on your own Hubble diagram. This is where the map analogy becomes more than a hook, because it predicts a specific observational relationship. If every separation stretches by the same factor, then farther points separate faster in terms of rate of change of proper distance. Hubble's law is what a stretching map looks like in data. The sky, in other words, behaves like a coherent system rather than a random scattering. The Hubble constant is the present-day expansion rate, and its units encode the idea in a compact way. It is measured in kilometers per second per megaparsec, which is speed per distance. That odd unit is a clue, because it is not a simple velocity like kilometers per second. It is a rate of change of scale, a fractional stretching per unit time. A megaparsec is about 3.26 million light-years, and that number is large enough to swallow our everyday sense of distance. So h0 tells you how many kilometers per second of recession you get for each megaparsec of separation. If h0 were 70, then two galaxies 1 megaparsec apart receded about 70 kilometers per second, on average. At 10 megaparsecs, the recession is about 10 times larger, because the expansion applies uniformly. Because it is a rate, h0 sets a timescale that tempts us into an age estimate. If the expansion rate had been constant, The inverse of h0 would approximate the universe's age, giving a value on the order of 14 billion years. The real universe changes rate, slowing under matter's gravity and later accelerating under dark energy. Even so, the link remains strong, and h0 anchors our cosmic chronology. h0 also helps set the size of the observable universe in a given cosmological model, because expansion history determines horizons. Horizons determine what light has had time to reach us since the hot beginning. The number shapes our cosmic map, telling us how far we can see and what regions were ever in causal contact. In a sense, h0 helps define the scale of our ignorance as well as our knowledge. At this point, a new confusion often appears, and it is understandable because the equation looks like it invites it. If recession speed grows with distance, then sufficiently distant galaxies can recede faster than light. That sounds like relativity breaking its own rule, and it can feel like a contradiction hiding in plain sight. The resolution depends on what relativity actually forbids. Relativity's speed limit is local, applying to objects moving through space in a local inertial frame. No object outruns light in its local neighbourhood, and no signal passes a nearby observer faster than c. But general relativity allows the distance between far-separated co-moving points to grow faster than c, because that growth is not a local motion. The metric can change in a way that increases proper distance rapidly. Superluminal recession is not a galaxy blasting through space faster than light, as if it were breaking a cosmic traffic law. It is the metric expanding so that the proper distance increases rapidly, even while each galaxy remains locally well behaved. The photon still moves locally at c, and the rules of special relativity remain intact. The strangeness is global, not local, an effect of geometry. This is another place where language creates a trap, because we reuse everyday words for unfamiliar concepts. We call it speed, but it is not the same kind of speed as a car or a spacecraft. The word is shared, the concept is not. Cosmology often sounds like ordinary motion, and then it surprises us when ordinary intuition fails. The evidence for expansion is therefore not a single observation, and it is not a single plot in a textbook. It is a mesh of measurements that reinforce one another across methods and decades. Distances say galaxies are far, and their distribution is not confined to the Milky Way. Spectra say their light is stretched, and the stretching increases with distance in a systematic way. But to turn Hubble's law into a precise Hubble constant, we need accurate distances, not just relative ones. That brings us back to the distance ladder, and to the problem of calibration, because calibration is where cosmology earns its credibility. A small bias in brightness can become a large bias in distance, and a large bias in distance becomes a large bias in h0. Precision here is not a luxury, it is the whole game. C-feeds work well within and near the local group where individual stars can be resolved and monitored over time. Beyond that, individual C-feeds become hard to resolve, blending into the glow of their host galaxies. Dust can redden and dim their light, and crowding can make them appear brighter than they are. Metallicity effects also complicate the brightness estimate, because a star's chemical composition subtly affects its luminosity and colour. So cosmology adds another rung, one that can shine across much greater distances. Type Ia supernovae act as brighter standardizable candles, visible across hundreds of megaparsecs. They are thermonuclear explosions of white dwarfs in binary systems, triggered when a white dwarf approaches a critical mass, or when two white dwarfs merge. In a brief span, a single event can outshine an entire galaxy. Type Ia supernovae are not perfectly identical, and early on that imperfection limited their usefulness. Yet they can be corrected, because the shape of the light curve correlates with intrinsic luminosity. Brighter events fade more slowly, and dimmer ones fade more quickly, a relationship discovered through careful observation. With calibration, they become distance markers across a large fraction of the observable universe, and they populate the Hubble diagram with points far beyond Cepheid reach. The ladder then works in steps, each one leaning on the previous one for support. Parallax measures nearby stars geometrically, using Earth's orbit as a baseline. Parallax calibrates Cepheids, tying their periods to absolute luminosities. Cepheids calibrate supernovae, linking supernova brightness to true distance in host galaxies. Supernovae extend the Hubble diagram deep into the expanding universe, where redshift is large and the pattern is unmistakable. This is the local distance ladder approach to h0, And it is direct in spirit because it builds outward from nearby geometry. It uses astrophysical objects as rungs, and it tries to keep each rung transparent, yet it also accumulates systematic uncertainties at each handoff, because every calibration step carries assumptions about dust, stellar populations, and instrument response. The ladder is not one measurement, it is a chain of measurements. Modern teams refine each rung with relentless detail, because the remaining uncertainties are subtle and stubborn. They use space telescopes to reduce atmospheric noise and to sharpen resolution in crowded fields. They observe in infrared bands to reduce dust sensitivity, and they model dust extinction laws to correct what remains. They build large samples to average over environmental quirks, and they cross-check with independent anchors like masers. One famous anchor is water masers orbiting a supermassive black hole in NGC 4258, where nature provides a geometric laboratory. The masers trace a thin disk, and their velocities can be measured through Doppler shifts. Their proper motions can also be tracked, letting astronomers infer the disk's physical size and distance through geometry. That gives a distance with minimal reliance on standard candles, and it serves as a firm bolt in the ladder. Another anchor is the tip of the red giant branch method, which uses a sharp feature in stellar evolution. As low-mass stars climb the red giant branch, they reach a predictable luminosity before helium ignition changes their internal structure. That tip creates a characteristic brightness in a galaxy's stellar population, visible as an edge in a luminosity function. It provides an alternative calibration path for nearby galaxies, reducing dependence on Cepheid systematics. With these tools, the local universe yields a Hubble constant around the low to mid-70s in kilometers per second per megaparsec. The exact value depends on dataset choices, dust modeling, metallicity corrections, and which anchors are emphasized. The uncertainties have tightened dramatically, and the error bars have become small enough to make disagreement meaningful. When a number becomes precise, it can also become provocative. Now the story takes a turn, because there is another way to measure expansion that does not climb outward from nearby space. Instead of building from parallax to Cepheids to supernovae, we can look backward to the early universe. The cosmic microwave background becomes a fossil record, a screen of ancient light that covers the entire sky. It is not a point source, but a background, an afterimage of the universe when it was young. The CMB is the afterglow of the hot early universe, released when the plasma cooled enough for electrons and protons to form neutral hydrogen. Before that moment, photons scattered constantly off free electrons, and the universe was opaque like the interior of a star. When neutral atoms formed, scattering dropped, and photons streamed freely, carrying a snapshot of conditions. Those photons have been travelling ever since, stretched by expansion into microwaves. That snapshot is not perfectly smooth, and the imperfections are the point. It contains tiny temperature fluctuations across the sky, variations at the level of tens of microkelvin. Those fluctuations encode acoustic waves in the early plasma, driven by gravity pulling matter inward and radiation pressure pushing outward. The result is a pattern of peaks and troughs in the CMB power spectrum, a harmonic signature of an early cosmic oscillation. The pattern has a characteristic angular scale, often described as the apparent size of the sound horizon at recombination. That scale depends on how far sound waves could travel in the primordial plasma before photons decoupled. It also depends on the geometry of the universe and on the expansion history between then and now. In other words, the CMB is a ruler imprinted at early times, projected onto the sky by billions of years of expansion. If we assume a cosmological model, we can fit the CMB power spectrum and extract parameters that make the pattern self-consistent. The best fit yields matter density, baryon density, dark energy density, and the Hubble constant, among other quantities. This is not a direct ladder because it does not measure distances to individual galaxies step by step. It is an inference through a model, and the model's internal coherence is part of the evidence. In the standard lambda CDM model, the CMB implies a Hubble constant in the high 60s, typically around 67 to 68 km per second per megaparsec. Again, the exact value depends on analysis choices and on how foregrounds are removed from the microwave sky, but the central value is consistently lower than local ladder results. The disagreement is not a rounding error, it is a persistent offset. This mismatch is called the Hubble tension, and the name is appropriate because it has a narrative pull. It is not a tiny disagreement buried in noise, and it does not fade away as instruments improve. It persists as measurements sharpen, and it sits at a level that makes cosmologists uneasy. When two careful methods disagree, the universe is either hiding a mistake or revealing a new layer. The tension could be mundane, and scientists must treat that possibility with respect. It could be an unrecognized systematic error in Cepheid calibration, supernova standardization, or the treatment of dust and crowding. It could be a subtle bias in how we interpret the CMB, such as foreground contamination from our galaxy, or assumptions about recombination physics. In precision cosmology, even small modelling choices can move a parameter, but the tension could also be profound, and that is why it matters beyond a single number. If both methods are right, then the standard model is incomplete, at least in the way it connects early times to late times. Something about early universe physics or late time expansion might be missing. The Hubble constant would then be a clue, not just a measurement. Possible fixes have been proposed and none is yet decisive, which keeps the mystery alive. Early dark energy could briefly change the expansion rate before recombination, shrinking the inferred sound horizon. Extra-relativistic species could alter the radiation content, changing how quickly the early universe expanded. Modified gravity could change how structure grows, subtly shifting the interpretation of multiple datasets. Each idea tries to move the same lever without breaking the rest of the machine. Each proposal has consequences that must match other observations, and this is where cosmology becomes a tight web. Baryon acoustic oscillations trace the same sound horizon at later times, acting like a standard ruler in galaxy surveys. Large-scale structure and gravitational lensing constrain how matter clumps and how light bends across cosmic time. The universe is overdetermined, and that is a strength, because it makes it difficult to fix one problem by creating another. So the Hubble tension becomes a narrative engine, and it sharpens the chapter's central theme. The universe is expanding, and we can measure it in more than one way. Yet the exact rate depends on how we ask the question, and that suggests hidden complexity. Are we missing a correction in our astrophysics, or are we missing a term in our cosmology? This is where we return to the phrase expanding into nothing, because the tension tempts us to reach for intuitive pictures. The data do not show galaxies flying into an external emptiness, like sparks into a dark room. The data show a relationship between distance and redshift across the sky, and that relationship looks the same in every direction. The universe's behavior is not oriented toward an edge. If expansion were motion through pre-existing space, we might expect a center and an edge in the pattern, or at least a directional asymmetry. We do not see that on large scales. We see isotropy, meaning the sky looks statistically similar no matter where we point our telescopes, once local structure is averaged out. We also see a law that looks the same in every direction, which is exactly what a uniform scale factor predicts. The better interpretation is that the scale factor changes everywhere, not just in some region pushing outward. Space is not a container that galaxies move through toward a boundary. Space is the set of distances that the metric assigns between co-moving world lines, and that metric can evolve. When the metric evolves, the meaning of separation evolves with it. When we say the universe expands, we mean the metric evolves with time, and proper distance between galaxies increases even if their co-moving coordinates stay fixed. The growth is internal, not into an outside. It is a change in the relationship between events in space-time, not a migration into a surrounding arena. The word expand remains, but the mental picture must be rebuilt. This does not make the word nothing irrelevant, and it does not banish the philosophical itch that started the chapter. It changes what nothing could mean, and it narrows the options. Nothing is not a region beyond the edge, because the data do not point to an edge. It is closer to the idea of vacuum, geometry, and the absence of a background stage, a universe that does not need an external room. The observable universe is the part we can see, not the totality of what exists, and that distinction matters for how we imagine boundaries. Its boundary is a horizon, not a wall, defined by light travel time and expansion history. We do not see beyond it not because something blocks our view, but because signals have not had time to reach us. The horizon is an information limit, drawn by physics. As expansion accelerates, horizons change, and the future sky becomes different from the present one. Some galaxies will eventually slip beyond what can ever influence us again, even if we keep watching forever. Their light can still arrive for a time, but new light emitted later may never reach us. The observable universe becomes a dynamic concept, tied to the expansion history and to the fate of cosmic communication. So the evidence forces two conclusions at once, and the pairing is what makes it unsettling. First, the universe is not static, because redshift and distance correlate in a systematic way that repeats across the sky. Second, our intuitive picture of expansion as motion into space is inadequate, because the pattern does not single out a direction or a center. The universe expands, but it does not expand like an explosion in a room. We can now state the central question with sharper edges, because the measurements have done their work. What does cosmic expansion actually mean in general relativity, where geometry is not a passive stage? How can the scale of space change without an outside space to change into? And if the expansion rate is still debated, what does that say about the completeness of our model? The measurements point toward a theory where geometry is physical, with dynamics tied to energy and pressure. Hubble's law hints at a uniform stretching described by a scale factor, and the redshift relation ties that factor to what we observe. The Hubble constant becomes a parameter in equations, not just a number in a table. It is a summary of how the universe behaves today and a clue to how it behaved before. To understand why redshift tracks the scale factor, we need spacetime, not only space, because time is part of the geometry that evolves. To understand why the expansion rate depends on energy content, we need general relativity's field equations, where matter tells spacetime how to curve. The evidence, therefore, becomes a bridge, carrying us from a linguistic paradox to a dynamical framework. It also carries a warning that the framework might be incomplete, and that the next step is not comfort but deeper structure. Next, we follow the redshift trail into the mathematics of spacetime, where expansion becomes geometry with consequences. Our task is to separate language from physics, then let physics reshape language. Chapter 2 anchored expansion in redshift and the Hubble law, then left us with a deeper demand. If distance grows because the metric changes, what is the metric, physically and operationally? If space itself evolves, why do we keep picturing an edge moving outward? That edge picture is stubborn because it matches ordinary experience, and ordinary experience is persuasive. Fireworks expand into air, ink spreads through water, and shock waves race across a surface. In each case, there is a background arena that stays put while things move within it. Cosmology asks us to drop that background, and the request can feel almost like a trick. Part of the confusion comes from language that was built for objects, not for geometry. We talk as if space were a substance that could be pushed, pulled, or piled up. Yet in relativity, the space in spacetime is closer to a bookkeeping system for measurements. It is the network of relationships that tells rulers and clocks how to behave. General relativity begins by refusing the old split between stage and actors. Space and time are not a fixed container where matter happens to move. Space-time is a physical geometry that can bend, stretch, and respond to what it contains. In this view, geometry is not scenery. It is part of the cast. Historically, this was a radical break from Newton's comfortable scaffolding, and it did not arrive overnight. Newtonian space was absolute, the same everywhere, and time ticked forward identically for all observers. Even when Newton spoke cautiously about causes, his equations assumed a universal stage that never changed. Einstein replaced that certainty with a rule. Measurements depend on the geometry you inhabit, and the geometry depends on what is present. Einstein's field equations compressed the idea into a rule that is easy to say, harder to internalize. Matter and energy tell spacetime how to curve. Curved spacetime tells matter how to move. The equations do not merely decorate gravity with geometry. They replace gravity with geometry. The slogan is not poetry, because it cashes out in the behavior of clocks and rulers. A clock deeper in a gravitational well ticks more slowly relative to one far away. A ruler laid across curved geometry does not add up the way Euclid trained us to expect. Even the idea of the same length becomes a question you answer by specifying a path and a time. In general relativity, straight is not a visual intuition but a definition. A straight path is a geodesic, the trajectory that extremises proper time for massive objects. Proper time is what an ideal clock measures along its own world line, and it is the closest thing relativity has to an objective duration. When space-time is curved, geodesics that begin parallel can converge or diverge, and freefall becomes the natural motion. This is not just a story about planets, although that is where most people first meet it. Mercury's orbit precesses because the Sun curves space-time, slightly twisting the geometry of near-solar trajectories. Light bends around massive bodies because photons also follow geodesics, even though they have no rest mass. In images, the effect looks like a lensing arc, but in the equations it is geometry doing bookkeeping. The operational meaning goes deeper than bending paths, because the metric also defines what now means. Curvature changes what equal time slices are, which changes how we compare distances across space. If two observers disagree on simultaneity, they can disagree on what the distance right now even means. That is not philosophical. It is a measurable consequence of how clocks synchronize. A planet orbiting a star is the familiar example, but cosmology uses the same logic at larger scale. Replace a single star with a nearly uniform cosmic fluid of matter, radiation, and pressure. Ask what geometry is consistent with that content. Then ask how that geometry evolves when the contents thin out and cool. Cosmic fluid is not a claim that galaxies are literally a smooth liquid. It is a mathematical coarse graining, an averaging over vast volumes so that clumps and voids blur into an effective density. On scales of hundreds of millions of light-years, that approximation becomes surprisingly accurate. The lumpy details remain real, but the large-scale equations track the average. The key conceptual shift is that geometry is dynamical, not decorative. The universe does not expand like gas filling a room. The universe expands when the metric that defines spatial distance evolves with cosmic time. In other words, the rule for converting coordinates into measured lengths changes. The metric is the rulebook for space-time intervals. It tells you how to compute the invariant separation between nearby events, combining space and time into one quantity. That invariant is what all observers can agree on, even when they disagree about coordinates. When the metric changes with time, the meaning of 1 meter between distant comoving points changes with it. To make that statement concrete, cosmology chooses a simple symmetry as a starting point. On large scales, the universe looks homogeneous and isotropic, averaged over galaxies and clusters. Those symmetries restrict the metric to the Friedmann, Lemaitre, Robertson, Walker form. It is a choice that is pragmatic, not naive, because it captures what the sky actually suggests. The name carries a quiet history of its own, and it reflects a debate that once mattered. Friedmann and Lemaitre showed that Einstein's equations naturally allow expanding solutions, even before Hubble's observations made expansion unavoidable. Lemaitre even connected expansion to redshift while the idea still sounded speculative. Robertson and Walker later clarified the general symmetry-based form, turning intuition into a standard tool. In that metric, the expansion is captured by a single function of time. The scale factor sets how big spatial separations are on a given cosmic time slice. When the scale factor grows, proper distances between co-moving points grow with it. The expansion is not something galaxies do, it is something the geometry does. Proper distance is the distance you would measure with an ideal chain of rulers laid along a spatial slice. It is not a coordinate label, and it is not a guess based on brightness. It is a geometric quantity defined by the metric, and it changes if the metric changes. The definition sounds abstract, but it is exactly what distance means in a curved spacetime. Co-moving points are not special locations in space, they are world lines carried with the cosmic flow. A galaxy can be co-moving even while local gravity binds its internal structure. The coordinate label can stay fixed while the physical distance to other labels increases. Co-moving is, in effect, the coordinate system that rides along with the average expansion. Visually, imagine a faint grid drawn across the cosmos, with galaxies pinned to grid intersections. The galaxies do not crawl across the grid like ants on paper. Instead, the grid spacing itself grows, and the separation between intersections increases everywhere at once. If the camera zooms out, the pattern stays centered on every observer. This is metric expansion, and it answers the central question by changing what the word expand refers to. Expansion is not motion through space, like debris flying outward. Expansion is the stretching of the distance rule that space uses internally. It is a change in the geometry that defines far apart. If the rule changes everywhere, the question into what starts to dissolve. You do not need an external region for the metric to evolve. You only need space-time itself to have dynamics, which general relativity supplies. The model does not demand a surrounding emptiness, because the model already includes what emptiness means. The Hubble law then becomes a geometric statement, not a blast wave statement. Recession speed is proportional to distance, because the same fractional stretching applies everywhere. Farther objects recede faster because there is more stretch space between us. The relationship is a fingerprint of uniform expansion, not a sign of a central detonation. That proportionality is often written as v such hd, but the symbols can hide the idea. H is not a fixed speed limit, and v is not a jet-like velocity through space. It is the rate at which proper distance grows at a given cosmic time. Over cosmic history, h itself changes as the contents of the universe change. There is also a subtlety that helps the intuition, and it matters for how we picture velocity. Nearby galaxies have small recession speeds, so the difference between moving through space and space expanding can look minor. At great distances, the difference becomes decisive, because the metric description remains consistent when naive motion pictures break. The farther you look, the more geometry takes over from common sense. This also explains why there is no center in the pattern. In a uniform expansion, every co-moving observer sees other co-moving observers receding. The symmetry is built into the metric, not assigned to a privileged location. A center would be a special place, and the large-scale equations do not single one out. If you stand in one galaxy and measure redshifts, you infer that you are surrounded by recession in every direction. If you repeat the experiment from another galaxy, the same pattern appears again. The universe does not hand out a special coordinate origin, and the equations do not require one. The center is a feature of certain pictures, not a feature of the physics. So where did the Big Bang happen if there is no center? In this framework, the Big Bang is not a point in pre-existing space. It is a limit in time where the scale factor becomes very small and densities become very large. It is an everywhere-at-once condition on a whole spatial slice. The phrase hot dense is not just rhetoric, and it is not only about matter. In the early universe, matter was ionized plasma, radiation was intense, and particles collided frequently enough to maintain thermal equilibrium. Temperature is a measure of typical particle energy, and the early cosmos was energetic everywhere. Light and matter were tightly coupled, trading energy so rapidly that the universe behaved like a glowing fluid. That sentence is the first diffusing move against the into what question. If the early universe is a hot dense state everywhere, then there is no edge where expansion begins. Every region we can observe was once closer to every other region, without any region being the origin. The beginning is a condition, not a location. It also changes what beginning means in practice. The story is not about a spark at a location, followed by matter rushing outward. The story is about an entire spatial slice evolving, with the scale factor acting like a global dial on distances. When the dial turns, everything moving separates, even if nothing locally flies. The usual explosion picture fails because explosions have a background. They expand into surrounding air or vacuum, and they have a boundary that advances. The Big Bang model does not require a background space outside the universe. If spacetime is the whole system, there is no external arena for it to occupy. Explosions also have a center you can point to afterward. Shrapnel trajectories trace back to a region, and the density of debris often falls with radius. In cosmology, the early density is not concentrated at a place, because place is part of what is being described. The geometry that defines place is itself evolving. Yet the mind keeps reaching for a boundary, because finite things usually have edges. Cosmology forces a distinction between finite and bounded. Something can be finite in extent and still have no boundary. That is not wordplay, it is a real possibility in geometry. This is where geometry becomes more than a metaphor. A boundary is a place where the rules stop, where you could in principle reach an edge and ask what lies beyond it. Finite but unbounded spaces have no such stopping point, even though their total size can be limited. The rules continue smoothly, and beyond never becomes a well-posed direction. This is where the sphere analogy earns its place, with strict limits. The surface of a sphere has finite area and no edge. You can travel in one direction and never meet a boundary, only return to where you started. The key lesson is about topology, not about shape in a surrounding room. Picture the camera gliding over a smooth, curved surface, with longitude lines converging at poles. No matter how far the camera moves, there is no cliff where the surface ends. The only surprise is that persistent motion can bring you back to your starting point. The sense of forward remains, but the space refuses to terminate. The analogy is not that the universe is a two-dimensional surface. The analogy is that geometry can be closed without being bounded. A three-dimensional space can be finite in volume and still be unbounded in the same topological sense. It can be self-contained, with no edge to fall off. In 3 dimensions, the closest cousin of a sphere's surface is a 3-sphere, a closed space with positive curvature. It is difficult to picture because it does not live as a surface in our everyday space. Yet its key property is simple: no edge, even with finite volume. If you could travel far enough, you would not find a boundary, only a return. The balloon image helps with one point and misleads with another. It helps because dots on the surface separate without a center on the surface. It misleads because the balloon sits in an external room, while the universe need not. The room is a visual convenience, not a physical requirement. When the balloon grows, you can point to the air around it and call that outside. In cosmology, that outside is not part of the model, and it is not demanded by the equations. The expansion is intrinsic, meaning it is defined entirely by relationships within the space. The metric changes, and distances respond from the inside. So we separate what the analogy teaches from what it smuggles in. It teaches that expansion can be intrinsic, defined by distances within the surface. It smuggles in an outside dimension that is not required by the equations. The discipline is to keep the first lesson and discard the second. A discipline metaphor is like a map with a legend. It tells you what corresponds to what, and it warns you where the correspondence ends. Without that discipline, the metaphor quietly reintroduces the very container space that general relativity removed. The mind gets its comfort back, but the physics gets distorted. General relativity allows several global shapes for space, even with the same local physics. Space can be flat, positively curved, or negatively curved, depending on total energy density and expansion history. Each case can still have no edge in the sense relevant to the paradox. The local laws can be identical while the global geometry differs. Flat space is the Euclidean case, where parallel lines remain parallel and triangles sum to 180 degrees. Negatively curved space is hyperbolic, where triangles sum to less than 180 degrees and volumes grow faster with radius. Positively curved space is spherical, where triangles sum to more than 180 degrees. These are not artistic labels, they are measurable statements about how geometry adds up. Flat space can be infinite, with no boundary and no center. Negatively curved space is also typically infinite, with more room than Euclid expects at large scales. Positively curved space can be finite, yet still unbounded like the sphere analogy suggests. In all 3 cases, edge is not automatically part of the story. Curvature here is not curvature into an external embedding space, which is another common trap. It is intrinsic curvature, measurable by triangles and parallel lines drawn within the space itself. The geometry is defined from within, without needing an outside reference. The universe does not have to be bent into anything to be curved. Intrinsic curvature has a practical meaning, even if we cannot draw cosmic triangles with chalk. In principle, you could infer curvature by comparing distances and angles across enormous scales. In practice, cosmology uses patterns in the cosmic microwave background and large-scale structure as its measuring tools. The sky becomes a survey instrument, and statistics become our rulers. Observations suggest the universe is very close to spatially flat on large scales. That does not automatically tell us whether the whole universe is infinite. It tells us that any curvature radius is large compared to the observable region. The cosmos, at least within our horizon, behaves like a nearly Euclidean stage, except the stage itself evolves. This is an important humility clause in the narrative. Close to flat means that within our horizon, geometry looks Euclidean to high precision. Beyond the horizon, the global topology could still be more complicated, and our data would not directly reveal it. The observable patch can be a small window onto a much larger structure. This brings us to the next crucial distinction, because our access to the universe is limited. The observable universe is not the whole universe, even if the whole universe is all that exists. The boundary of observation is a horizon, not an edge of space. It is a limit set by causality, not by topology. A horizon is created by light travel time combined with expansion history. Light has a finite speed, and the universe has a finite age since the hot beginning. There are regions whose light has not had time to reach us, and regions whose future light may never reach us. The horizon is a record of what signals can do, not what space is. The first kind is often called the particle horizon, the limit of what we can see today. The second kind is related to an event horizon, the limit of what can ever influence us if accelerated expansion persists. Both are about causality, not about a wall at the end of space. They are boundaries in our information, not boundaries in existence. To visualize it, imagine a dark ocean at night, with a lighthouse beam sweeping across the water. The beam has travelled only so far, so the illuminated region is limited. The darkness beyond is not a boundary of the ocean, only a boundary of the light. The ocean can continue, indifferent to what the beam has reached. So when people ask what is beyond the observable universe, they are asking a legitimate question. Beyond our horizon, there may be more of the same spacetime, more galaxies, and more cosmic history. That question is about unseen regions inside the universe, not about an outside of the universe. It is the difference between unseen and non-existent. The difference matters because it changes the kind of answer science can offer. Beyond the horizon is a statement about what is currently unobservable, which may still be modelled and constrained indirectly. Outside the universe is a statement about a hypothetical container, which the standard framework does not include. One question can be sharpened by data, the other dissolves under definitions. The word outside implies a surrounding space that contains the universe as an object. General relativity does not require such a container, and the standard cosmological models do not include it. The universe can be all of spacetime, so outside becomes a category mistake. The model has no coordinate for beyond spacetime, because spacetime is the coordinate system. That phrase, category mistake, is not meant to shut down curiosity. It is meant to redirect it toward questions the theory can actually pass. If spacetime is the totality of locations and times, then outside spacetime is like north of the North Pole. The words sound grammatical, but the map has no such direction. Still, the intuition that expansion needs room is stubborn, because in daily life geometry is fixed. In relativity, geometry is physical, and it can change. The room is not a separate entity, it is the metric itself. The universe does not expand into a container, it updates the rule that defines separation. When we say space stretches, we are not describing rubber being pulled by invisible hands. We are describing the evolution of the scale factor in the metric, which changes the mapping from coordinates to measured distances. The stretching is a statement about measurement, not about substance. It is what rulers would report if you could lay them across cosmic distances. The Friedmann equations make that dependence explicit in a compact way. They connect the expansion rate to energy density, pressure, and curvature. They show that expansion is not arbitrary. It is a dynamical response to what the universe contains. The equations are, in effect, the universe's balance sheet. In these equations, the expansion rate is encoded in how quickly the scale factor changes with time. Energy density appears because mass energy gravitates, and pressure appears because pressure is also a source of gravity and relativity. That last point often surprises people, because pressure is not a gravitational source in Newton's simpler picture. In relativistic terms, squeezing can weigh. Matter slows expansion because its gravity attracts and resists separation. Radiation also gravitates, and its pressure matters strongly in the early universe. Dark energy can accelerate expansion because negative pressure contributes to gravity with the opposite sign. The same formalism that predicts deceleration under matter can predict acceleration under a different component. The sign flip is not magic, it is bookkeeping in the stress-energy tensor. In relativity, energy density and pressure both shape curvature, and sufficiently negative pressure can drive accelerated expansion. In plain terms, the contents of the universe can make the expansion speed up. The universe's fate is written in what fills it. This is where the space-time fabric metaphor can help, if we keep it disciplined. Fabric is not a substance floating in a larger void. Fabric is a way to say geometry has elasticity-like behavior under stress energy. It is a metaphor for responsiveness, not for material threads. The metaphor works best when the visuals stay abstract. A grid of lines can bow near a mass. and the spacing between lines can increase as the scale factor grows. The viewer sees relationships changing, not a sheet being pulled into a surrounding emptiness. The emphasis stays on intrinsic distances, not on an imagined outside. But fabric metaphors can also mislead, because real fabric stretches into surrounding space. Spacetime does not need an external place to stretch into. The metric defines the very notion of distance that stretching refers to. If the metric changes, more room is created internally, because the definition of room has changed. So the central question now has a sharper form that the equations can address. What does it mean for the scale factor to increase if there is no external coordinate space? It means that the invariant distance between comoving world lines changes with cosmic time. The change is real because it is tied to what ideal measurements would yield. Invariant is doing real work here. It means the distance is not a coordinate artifact, not something that disappears when you relabel points. It is a quantity tied to the metric, and different observers can agree on it when they use the same cosmic time slicing. The agreement is not perfect in all situations, but in the FLAW setting it becomes a clean standard. We can even say what is not changing in this description. Galaxies are not generally moving through space away from a central origin. They are largely at rest in comoving coordinates, while the proper distance between coordinates increases. The motion is in the geometry, not primarily in the matter. This is why the language of recession is both useful and dangerous. It is useful because it describes increasing separation. It is dangerous because it invites the mental picture of rockets flying away from a blast site. The safer picture is separation growing because the ruler you would use is being rescaled. Local physics remains local, which is why atoms and solar systems do not expand. Bound systems decouple from the Hubble flow because their internal forces dominate. Expansion is a large-scale property of the metric, not a universal stretching of everything. The same universe can expand overall while leaving small structures essentially unchanged. There is a scale dependence built into the story. Within a galaxy, gravitational binding and orbital dynamics set the geometry that matters for motion. Between galaxies, where the average density is low and the cosmic fluid approximation applies, the FLRW expansion becomes the right description. The transition is not a sharp border, but the hierarchy is clear. This also clarifies why superluminal recession is not a violation of relativity. Relativity forbids objects from outrunning light locally through space-time. It does not forbid the metric from evolving so that distant proper distances grow faster than c. The limit is on local speeds, not on global separation rates. If two distant galaxies are separated by enough expanding space, their proper distance can increase at a rate exceeding c. No one in either galaxy measures nearby objects breaking the light speed limit. The faster than light is a global statement about distance change, not a local chase. It is the difference between how fast a river widens and how fast a boat moves. So far, general relativity has done what we asked of it. It reframes expansion as geometry, removes the need for an outside, and explains the lack of a center. It also gives us a clean language for finite versus infinite, and for horizons versus edges. The paradox softens because the model stops asking for a container. It also gives us a new kind of visual storytelling. The camera can pull back from a cluster of galaxies to a web of filaments, then fade into a coordinate grid whose spacing slowly grows. The viewer watches the rule of distance change rather than watching matter fly into emptiness. The expansion becomes a quiet, pervasive transformation. But general relativity also plants a warning sign at the beginning of the story. If we run the equations backward in time, the scale factor shrinks and densities rise. In many solutions, curvature invariants blow up at a finite time in the past. The mathematics does not merely suggest difficulty, it announces a limit. Running backward is not just a cinematic rewind, it is a mathematical extrapolation. The same equations that fit today's expansion can be integrated into the past, and they lead to a regime where the classical description becomes extreme. The warning sign is written in the language of divergence. It is as if the map's grid lines crowd together until the map itself stops making sense. That blow-up is what we call a singularity, and it is often described badly. It is not necessarily a literal point in space where everything piles up. In cosmology, it is a signal that the classical description has reached its limit. The equations are still being applied, but the assumptions behind them are breaking. To be precise, the troubling feature is not merely large numbers, but the breakdown of geodesic completeness. World lines that represent freely falling observers cannot be extended indefinitely into the past. The spacetime, as described by the classical metric, simply ends along those paths. In a theory built on smooth geometry, that ending is a red flag. A singularity in general relativity is a breakdown of the theory's predictive power. Geodesics cannot be extended in a well-defined way, and physical quantities diverge. The mathematics is telling us that something is missing from the model. It is less like a dramatic object and more like a torn page in the rulebook. In other areas of physics, divergence often signals that we used an approximation beyond its range. Classical fluid equations fail at molecular scales, and classical electromagnetism fails when quantum effects dominate. The singularity suggests that spacetime itself may have a deeper description. It hints that the smooth metric may be a large-scale average, not the final layer. So the Big Bang singularity is not automatically a claim about an actual infinity in nature. It is a signpost that our equations are being pushed beyond their domain. It is the place where quantum effects are expected to matter. The word beginning becomes a placeholder for unknown physics, not a settled conclusion. Quantum effects here are not an optional detail, because the early universe involves enormous energies in tiny volumes. At sufficiently high densities, the quantum behavior of fields cannot be ignored, and the gravitational field may need a quantum description as well. The classical metric may be an emergent large-scale approximation. If so, the fabric could have a microscopic weave that we have not yet observed. This is where the chapter's mystery deepens rather than resolves. General relativity explains how expansion can happen without an outside. Yet the same theory predicts its own failure when we ask about the universe beginning. The framework is powerful, but it is not self-sufficient at the earliest times. There is an almost narrative irony in that. The theory that removes the need for an external stage also refuses to give a complete account of the first act. It offers a coherent middle, then points to the opening scene and says, "Here, my language breaks." The silence is not evasive, it is structural. We can now state the tension in one line that sets up the next chapter. The spacetime fabric can stretch without expanding into anything. But at the earliest times, the fabric description itself may tear. The question shifts from where is the edge to what replaces the fabric. That tear is not just philosophical, because it affects what we mean by time and origin. If cosmic time begins at a singularity, then asking what happened before becomes ill-posed within the theory. If the singularity is replaced, then the universe beginning may be a transition, not a boundary. The difference is the difference between a wall and a doorway. Notice how the question subtly changes. Instead of what was outside, we ask what replaces the classical metric, and what counts as before when time itself is part of the system. Those are still mysterious questions, but they are questions with a clearer target. They invite physics, not just imagery. Inflation enters here as both a solution and a complication. It's an episode of accelerated expansion driven by a high-energy field state. It can smooth curvature, dilute relics, and set initial conditions for structure. It also changes the way we narrate the early universe, because it inserts a dramatic geometric transformation. The idea emerged to address puzzles that look like horizon problems and flatness problems. Why does the cosmic microwave background have nearly the same temperature in regions that seem causally disconnected in a simple expansion history? Why does the universe appear so close to spatially flat rather than strongly curved? These puzzles are, at their core, questions about initial conditions and causal contact. Inflation also changes how we think about horizons and causal contact. It can place regions now far apart within a once causal patch, explaining large-scale uniformity. It can also push regions beyond each other's horizons, making parts of the universe permanently unobservable. The same mechanism that explains sameness can also create separation. In visual terms, inflation is a dramatic zoom. A tiny region, once in thermal contact, is stretched so much that it becomes larger than the observable universe today. The smoothing is not a gentle settling. It is an exponential expansion that flattens irregularities the way stretching a wrinkle can make it disappear. The camera would see small ripples fade into near-perfect uniformity. Then later, faint patterns re-emerge as structure grows. Yet inflation does not automatically remove the singularity in every model. Some inflationary spacetimes are past incomplete, meaning they still require new physics at the beginning. The question becomes what replaces the singularity, not whether the universe needed an outside. Even the most successful patch can leave the first stitch unresolved. So we end with a reframe paradox that is sharper and more productive. The universe is not expanding into nothing, because expansion is an internal change of geometry. The real mystery is what spacetime is made of, and what happens when classical geometry fails. If the metric is a field, what is its underlying degree of freedom? At this point, it is worth pausing on a thought that is easy to miss. We have treated the metric as a field, something with dynamics and equations of motion. If it is a field, then perhaps it has quanta, fluctuations, and a microscopic structure we have not yet seen. If so, the early universe may not be a singular point, but a regime where the notion of smooth distance is replaced. Next, we step toward quantum ideas, where vacuum is not empty and beginnings can be reimagined. We follow the singularity signpost into the territory where space-time, time, and nothing are all up for renegotiation. Chapter 3 reframed expansion as geometry, not motion into an external container, and that shift breaks the language trap by replacing "into what" with how distances are defined. Yet the moment we accept that reframing, the early universe stops feeling like armchair philosophy and starts resembling forensic science: evidence, constraints, and a timeline reconstructed from faint signals. When we look outward in every direction, we see the cosmic microwave background, the CMB, as a nearly perfect black-body glow that arrives from the edge of the observable past. It is the cooled remnant of a time when matter and radiation were tightly coupled, constantly scattering, constantly exchanging energy, and behaving like a single hot fluid. Today that glow sits at about 2.725 Kelvin, and it fills the sky with an almost eerie uniformity that no ordinary astrophysical source could easily imitate. A black-body spectrum is not just warm light, because it is a very specific curve that encodes thermal equilibrium. The CMB's spectrum matches that curve with extraordinary precision, which tells us the early plasma was once dense enough to erase memory of how it began. In the language of physics, repeated interactions drove the radiation toward a Planck distribution, the same statistical shape that emerges in furnaces and stellar interiors. That is why the CMB is so valuable. It is not merely old light, it is light that remembers being thermal. On a full sky map, the temperature varies only by tens of microkelvin from place to place, and those variations are so small that they are easy to underestimate. A few parts in 100,000 sounds like a technical detail, until you recall that the early universe was a cauldron of relativistic particles and intense gravitational dynamics. The uniformity is not just a curiosity for specialists, because it functions like a demand written into the data, an instruction that the early cosmos must have shared information efficiently. Visually, imagine a sphere of faint orange light surrounding us, smooth like frosted glass, with the Milky Way's foreground cut away like a careful surgical mask. Then, as the map's contrast increases, tiny freckles appear, blue and red specks that mark minuscule hot and cold patches across the celestial dome. The more precisely we measure, the more that pattern becomes a fingerprint rather than noise, because the same statistical texture repeats across independent experiments. Those freckles are not random in the everyday sense, because their distribution carries structure across many angular scales. Some patches cluster into slightly larger regions, while others fade into finer grain, producing a hierarchy that can be quantified. That hierarchy is what lets cosmologists compress an all-sky image into a power spectrum, a kind of barcode for the early universe. The CMB is a picture, but it is also a dataset with a grammar. In the simplest hot Big Bang history, that smoothness is hard to justify without special pleading. Light and any other causal signal travel at a finite speed, and the universe has a finite age, so there is a limit to who can influence whom. Those two facts carve the early cosmos into regions that cannot talk to each other, even if the universe is homogeneous on average. The problem is not that the universe expanded, but that it did so while communication remained limited. The key idea is the particle horizon, the maximum distance over which information could have travelled since the beginning, given the expansion history. At the time the CMB was released, the universe was only about 380,000 years old, which is long by human standards but brief by cosmological ones. Before that moment, photons scattered off free electrons so frequently that the universe was effectively opaque, like a glowing fog. When electrons finally combined with nuclei and the fog cleared, The photons streamed freely, carrying a snapshot of conditions at that time. That clearing is recombination, but the more intuitive phrase is last scattering, because it marks the last time most CMB photons bounced off charged particles. The surface we see is not a literal shell, but a thin time slice with a small thickness, because decoupling took time. Even so, it is sharp enough that we can treat it like a cosmic photograph. We are looking at a moment when the universe first became transparent. Opposite sides of our sky correspond to regions that were separated by far more than one horizon length at that epoch. Once you translate angles into physical separations on that last scattering surface. In a straightforward expansion history, they could not have exchanged heat or equilibrated because there simply was not enough time, yet they look as if they share a single thermal narrative, as if the universe had time to settle into one temperature with astonishing precision. The sky appears coordinated where the simplest causal accounting says it should be fragmented. This is the horizon problem, and it is a problem of communication rather than measurement. How did regions that could not exchange energy end up with nearly identical temperatures? Not just roughly, but to 1 part in 100,000. Why does the CMB look like one coherent story, not many disconnected chapters stitched together by coincidence? The puzzle is sharpened, not softened, by the quality of the data. To feel the tension, picture 2 distant rooms that never shared air, never opened a door, and never exchanged a molecule even once. Now imagine both rooms somehow arriving at the same temperature to within 100,000th of a degree, despite having separate heaters and separate histories. That is the kind of coincidence the CMB seems to demand, except the rooms are horizon-sized regions of the young universe. If you take causality seriously, the uniformity becomes a clue that something is missing. The same data raises a second puzzle, and this one is about geometry rather than temperature. When we infer the large-scale shape of space, it appears extremely close to flat, meaning Euclidean geometry works astonishingly well on the larger scales we can test. Flat here does not mean featureless, because galaxies and clusters still curve spacetime locally and bend light into arcs and rings. It means that, averaged over immense distances, the global curvature is near zero to within tight observational limits. Curvature is not just a philosophical label, because it changes how volumes grow with radius, and how triangles add their angles. In a positively curved space, like the surface of a sphere generalized to 3 dimensions, parallel lines eventually meet, and triangles have more than 180 degrees. In a negatively curved space, like a saddle generalized to 3 dimensions, parallel lines diverge and triangles have less than 180 degrees. The universe seems to sit extremely close to the knife edge between those behaviors. In the Friedmann equations, that near flatness is not a generic outcome of ordinary evolution under matter or radiation. Curvature behaves like a term that can grow in relative importance as the universe expands, because different contributions dilute at different rates. Radiation energy density falls rapidly as the universe grows, matter falls more slowly, and curvature effectively falls at yet another rate. If the universe started even slightly curved, that curvature would tend to become more noticeable over time, not less, under standard decelerating expansion. The parameter that tracks this is often written as omega, the density parameter, which compares the actual energy density to the critical density needed for flatness. When omega equals 1, the universe is spatially flat in the simplest models, and the expansion is exactly balanced against the energy content. When omega differs from 1, curvature contributes to the expansion in a way that typically amplifies the deviation as the universe ages. The equations make the sensitivity explicit, and that sensitivity is what makes the flatness problem sting. So a nearly flat universe today implies something extreme about the past, because early deviations would have been magnified into obvious curvature by now. It suggests that omega must have been astonishingly close to 1 in the early universe, close enough that even tiny deviations would have ruined today's near flatness. This is the flatness problem, and it points directly at initial conditions that appear tuned to an almost absurd precision. The universe seems balanced as if it began with a cosmic level. There is also a third puzzle that sounds at first like a missing mess, a universe that is too tidy for its own good. High-energy theories often predict relics from early-phase transitions, when symmetries break as the universe cools and different forces separate their behaviors. Magnetic monopoles are the most famous example, because many grand unified theories produce them naturally as topological defects. They are not merely speculative ornaments, because their existence would be a deep statement about the structure of gauge fields. These relics are not mere curiosities because they would be heavy, stable, and extraordinarily difficult to destroy once produced. In a naive hot Big Bang picture, they should be produced abundantly, like sparks from a furnace, because the early universe passed through energies where such defects are expected. Yet we do not see them in the numbers those simple estimates suggest, and the absence becomes its own kind of measurement. The universe looks too clean, as if something diluted the debris before it could matter. The night sky is not crowded with exotic leftovers, and our detectors do not report the expected flux of monopoles passing through Earth. We also do not see other predicted defects in the abundance that many models would imply, though the details depend on the theory. This is the relic problem, and it hints at an eraser built into cosmic history, an episode that thinned out whatever was made too early. The puzzle is not that relics are impossible, but that they are missing where they were expected. These three puzzles, horizon, flatness, and relics, arrive as a linked set, because they all point to the same era when the expansion history was being written. They are not three unrelated complaints, because each one becomes severe when you extrapolate the standard model of cosmology backward to extreme conditions. The question becomes whether the early universe had an additional phase we have not yet accounted for, a phase that changes the causal and geometric bookkeeping. If the universe left an imprint, perhaps it also left a gap. Cosmology answers with a bold proposal called cosmic inflation, and the name is almost understated for what it claims. It is not the late-time acceleration from dark energy, and it is not a gentle speeding up of an already expanding cosmos. It is a brief episode of extraordinarily rapid, nearly exponential expansion in the very early universe, occurring long before the CMB was released. In many models, it happens around energies far beyond anything we can reach in accelerators. Historically, inflation emerged in the late 1970s and early 1980s, when theorists were trying to connect particle physics ideas to cosmology in a disciplined way. Alan Guth's early formulation was motivated by the monopole problem in grand unified theories, and it quickly became clear that the same mechanism could address horizon and flatness as well. Others, including Andre Linde and Paul Steinhardt, refined the idea into versions that could start and end more plausibly. The proposal was radical, but it was also economical, because one mechanism could address several problems at once. Inflation begins with a tiny patch of spacetime that is smooth enough to start, and the phrase smooth enough hides a real physical requirement. That patch is small enough to be in causal contact, so signals can cross it and homogenize it, at least approximately. In plain language, it is a region that has time to settle down before it is stretched, like a small droplet reaching a uniform temperature before being pulled into a thin film. The patch does not need to be perfect, but it must be coherent. Then its scale factor grows by an enormous factor in a tiny fraction of a second, and the numbers involved are difficult to hold in the mind. The scale factor is the cosmic ruler in the FLRW metric, the function that tells you how comoving separations translate into physical distances at a given cosmic time. When it grows, every comoving separation grows with it, not because objects fly through space, but because the metric changes and the meaning of distance changes. Inflation says that ruler did not just lengthen, it exploded. Exponential growth means the scale factor multiplies by roughly the same factor each short interval, so the expansion compounds rather than accumulates. Distances do not add, they multiply, and multiplication is how small beginnings become vast outcomes. In many scenarios, the universe expands by at least a factor of just 60 eons, which is a number so large that ordinary intuition fails. The point is not the exact count, but the fact that it is enough to transform microscopic scales into cosmic ones. A region that began smaller than an atom can be stretched to astronomical scales while remaining the same comoving patch, which is the subtle but crucial idea. The image is counterintuitive because nothing needs to outrun light locally, and no object has to break relativity in its own neighbourhood. Instead, the distance between far apart comoving points increases because the geometry between them expands, and general relativity permits that without contradiction. Relativity limits motion through space, not the growth of space's metric itself. This is the key maneuver that attacks the horizon problem, because it rearranges the causal story without changing the rules of causality. Before inflation, the patch was small enough for light and other signals to cross it, allowing it to share temperature and reach near equilibrium. After inflation, That once connected patch is stretched into many regions that are now far beyond each other's horizons. Even though they share a common origin, uniformity becomes inherited rather than negotiated later. The CMB looks smooth because it comes from a region that had time to homogenize before inflation, when it was still a single causal neighborhood. Inflation turns one small communicative domain into the backdrop of our entire sky. And it does so by making the later universe larger than the naive horizon accounting would suggest. The coincidence becomes a consequence, which is the kind of move physicists look for. The sky's uniformity stops being a miracle and becomes a memory. To visualize it, imagine a tiny grid drawn on a rubber sheet, with ink dots marking points that can exchange signals while they remain close. The sheet is then pulled so violently that the dots separate by enormous distances, even though the grid lines between them have simply stretched. The dots did not sprint, but the sheet did the work, and the ability to communicate existed only before the pull. When we see similar temperatures across the sky, we may be seeing the aftermath of that stretching. Inflation also attacks the flatness problem through stretching, but the argument is geometric rather than thermal. Curvature is a feature that becomes harder to detect when a space is blown up, because any small patch of a curved surface looks flatter when magnified. A globe looks curved in your hands, yet a small neighborhood can look nearly planar if you zoom in far enough. Rapid expansion drives the observable region toward near flatness in exactly that sense, by making any initial curvature radius enormous compared with what we can see. In the Friedman language, inflation drives the density parameter toward 1, effectively making flatness an attractor during the accelerated phase. Deviations from omega equals 1 are rapidly suppressed because the scale factor grows so quickly that the curvature term becomes negligible. The fine-tuning is shifted away from initial curvature and toward the conditions that allow inflation to occur, which is not the same as eliminating mystery. Still, it changes the kind of mystery, and it changes what the data seems to demand. The relic problem is handled by dilution, and the logic is brutally simple once you accept the scale of the expansion. Any unwanted heavy particles or topological defects are spread thin by the enormous growth, like a drop of dye dispersed into an ocean until it becomes undetectable. Their number density falls so dramatically that they become effectively absent in our observable patch, even if they were once abundant. Inflation does not need to forbid relics, it can simply make them rare. So inflation is introduced as a solution set, not as decoration, and the elegance is that the same expansion phase addresses 3 different complaints. It explains why the universe is smooth, why it is nearly flat, and why it lacks certain predicted relics, all by changing the early expansion history. It adds a short phase with very different dynamics, and it asks us to take the Friedman equations seriously in a regime where intuition is weakest. The question shifts from why is the universe like this to what could have powered that phase. But what drives such an extreme expansion in general relativity, where gravity is usually attractive and expansion usually slows under normal matter? GR ties expansion to energy density and pressure through the Friedman equations, which are the cosmological reduction of Einstein's field equations under symmetry assumptions. They tell us that gravity does not only respond to mass because it also responds to pressure, and in relativistic settings, pressure can be as important as energy density. The source of gravity is the stress-energy tensor, not just stuff. To accelerate expansion, the universe needs a component with sufficiently negative pressure, and that phrase can sound like wordplay until you connect it to the equations. In cosmology, pressure contributes to the gravitational source, and negative pressure can act like a repulsive term in the acceleration equation. A useful plain language translation is that the energy behaves as if it resists being diluted, so the expansion does not drain it the way it drains matter or radiation. When the energy density stays nearly constant while space grows, the expansion can feed on itself. Inflation proposes a field, often called the inflaton, that behaves like vacuum energy for a time, and the analogy is deliberate. Its energy density remains nearly constant even as the universe expands, which is unusual compared with matter, whose density drops as volume grows, or radiation, whose density drops even faster. Its pressure is negative, and in GR that negative pressure can drive accelerated expansion, producing a near exponential growth of the scale factor. The field is not introduced for drama, it is introduced because the equations demand something like it. We keep the inflaton concept accessible by focusing on its role, not its identity, because the role is what the data constrains. It is a high-energy state of a field that dominates the stress energy budget, meaning it overwhelms other contributions in that era. While it dominates, it makes the expansion accelerate dramatically, and it keeps doing so as long as the field remains in that state. In many models, the inflaton changes slowly enough that the expansion is smooth, which matters for the uniformity we observe. Qualitatively, the first Friedman equation links the expansion rate to the energy density, telling you how fast the cosmic ruler grows. The second links the acceleration of the scale factor to energy density plus 3 times pressure, a combination that matters deeply in relativistic gravity. If pressure is negative enough, that combination becomes negative and the acceleration becomes positive, which is the mathematical signature of inflation. The sign flip is the heart of the mechanism. This is the same sign logic that later appears as dark energy, but at a vastly higher energy scale and for a vastly shorter time. Inflation is an early vacuum-like phase, not a permanent one, and it must end because our universe is not an eternally inflating empty, de sitter space. If it did not end, the universe would never reheat into the hot plasma we know, and there would be no nucleosynthesis, no atoms, and no CMB. The end is not optional. It is part of the story. Ending inflation is as important as starting it, because the universe we observe is not empty and not cold. The inflaton must transition from its vacuum-like state into ordinary particles and radiation, converting stored energy into a thermal bath. That conversion is called reheating, and it repopulates the universe with heat, entropy, and the ingredients for later structure. It is the bridge between the inflationary phase and the familiar hot Big Bang evolution. Reheating connects inflation to the standard hot Big Bang, and it explains why the universe after inflation is hot, dense, and filled with radiation, setting the stage for nucleosynthesis and later recombination. Without reheating, inflation would leave a cold, nearly empty, rapidly expanding spacetime with little to evolve. With reheating, the universe becomes a plasma again, and the clock of conventional thermal history can start ticking. The CMB then becomes a later snapshot of a universe that was reheated long before. Inflation is often described with a potential energy landscape for the inflaton, because potentials are how fields store energy in quantum field theory. The field slowly rolls along that potential, and during the slow roll phase, its potential energy dominates over its kinetic energy. That dominance keeps the energy density nearly constant, which is what sustains quasi-exponential expansion over many e-folds. The slow in slow roll is not about speed through space, but about how gently the field value changes in time. Then, as the field approaches a lower energy state, the slow roll conditions break and the dynamics change character. The inflaton can oscillate and decay into other particles, transferring energy into a hot bath through couplings that depend on the underlying particle physics. The details vary across models, and that variation is part of the modern uncertainty, because we do not yet know which couplings nature chose. In narration terms, inflation is a framework with many scripts, and the universe may have chosen one we have not yet pinned down. Some models use a single field, others use multiple fields that interact, and the difference can change the predicted pattern of fluctuations. Some end smoothly, while others end through instabilities that can be abrupt, even violent, producing bursts of particle production. Even the temperature reached after reheating can vary, and that matters for what kinds of particles could have been produced. The broad arc remains consistent, but the microphysics is still an open file. Inflation does more than solve problems, it makes predictions, and the most famous prediction is that quantum fluctuations are unavoidable. Quantum fields cannot be perfectly still, even in their lowest energy state, because uncertainty relations forbid exact zero motion in field variables. Even a vacuum-like state has fluctuations in field values, and those fluctuations are not optional, they are built into quantum theory. Inflation takes those microscopic jitters and gives them room to matter. During inflation, microscopic quantum fluctuations are stretched to astronomical scales, and the scale change is the whole trick. A fluctuation that began far smaller than an atom can be blown up until it spans a region that later becomes galaxy-sized and then larger still. Inflation turns quantum noise into cosmic structure, and it does so by making the expansion act like a magnifying lens that freezes patterns in place. What begins as a probabilistic ripple becomes a classical-looking seed. The mechanism is simple in outline, even if the calculations are subtle, and require careful treatment of quantum fields in curved spacetime. Fluctuations in the inflaton and in the metric create tiny variations in energy density and curvature, which translate into slightly different gravitational potentials. When inflation ends, those variations become classical-looking seeds, because their wavelengths have been stretched beyond the horizon and effectively freeze in. Later, as the horizon grows, those modes re-enter and begin to influence matter again. After reheating, matter and radiation respond to those seeds, and gravity amplifies the slightly denser regions over billions of years. Denser patches pull in more material, deepening the contrast, while underdense regions become cosmic voids. Galaxies, clusters, and the cosmic web emerge from these primordial ripples, like a photograph developing from a faint latent image. The large-scale universe becomes a map of amplified early irregularities. This links inflation to the Chapter 2 theme that the sky keeps receipts, because the CMB is not perfectly uniform and its tiny anisotropies are the fossil imprint of those early fluctuations. When we map them, we are not merely making a picture, because we are reading an encoded record of early universe physics. The CMB is a ledger of initial conditions, written in temperature and polarization. It is also a test of whether inflation's story matches nature's handwriting. On screen, the CMB map can be shown as a sphere that slowly rotates, with color differences exaggerated to reveal structure, while the underlying glow remains smooth. The smooth field resolves into a stippled pattern, and then into a hierarchy of angular scales that feels almost like terrain. Each scale carries information about what the universe was doing long before atoms formed, because different scales correspond to different physical wavelengths at last scattering. The visual can linger long enough for the audience to feel that this is not art, but measurement. Inflation predicts a specific statistical character for that imprint, and statistics are where cosmology becomes precise. The anisotropies are measured as a power spectrum across angular scales, often plotted as peaks and troughs that rise from a baseline. Those features appear because the early plasma supported acoustic oscillations, essentially sound waves in a hot, dense fluid of photons, electrons, and baryons. Gravity tried to compress overdense regions. Radiation pressure pushed back, and the competition produced oscillations. The peaks are not arbitrary bumps because their positions and heights encode physical scales and composition. The first peak corresponds roughly to the largest sound wave that had time to compress once by recombination, and the subsequent peaks reflect higher harmonics. Their relative heights carry information about baryon density, dark matter density, and the overall geometry of space. When the peaks line up the way they do, they tell a consistent story across independent parameters. Inflation sets the initial conditions for those oscillations as nearly scale-invariant and adiabatic perturbations, and those words are technical but interpretable. Scale-invariant means that fluctuations have almost the same strength across a wide range of scales, with a slight preference for larger scales in many models. Adiabatic means different components fluctuate together, like a single fluid, rather than competing ingredients with independent randomness. These are the initial conditions that produce the clean, coherent peak structure we observe. A key parameter is the spectral index, which measures how fluctuation power changes with scale, and it is one of inflation's most quoted quantitative successes. Inflation broadly predicts a spectrum close to scale, invariant, but not exactly, because slow roll dynamics introduce a small tilt. Observations find a slight tilt away from exact scale invariance, consistent with many slow-roll inflation models, and the agreement is not vague. It is a numerical match within tight error bars, which is rare in early universe speculation. Another prediction concerns phase coherence, and this is where the CMB becomes almost musical. The acoustic peaks in the CMB are sharp and regularly spaced, and that spacing is not an accident of data processing. It indicates that the perturbations began with a coherent phase, like a synchronized set of oscillators that all started their cycles together. If the initial conditions were messy or continuously sourced, the peaks would smear out into a softer ridge. Inflation naturally produces that coherence because the perturbations originate from stretched quantum fluctuations that become superhorizon and then re-enter later with a well-defined phase relationship. Competing non-inflationary mechanisms struggle to produce the same clean peak structure without extra assumptions, because they often generate perturbations in a more causal, continuously driven way. The peaks become part of inflation's evidence trail because they look like the output of a specific kind of beginning. The universe oscillated, and it did so in rhythm. Inflation also predicts that perturbations should be nearly Gaussian, meaning their statistics are close to those of a simple random field. In a Gaussian field, the two-point correlation function or power spectrum captures almost all the information, and extreme outliers are rare. Current data shows the CMB is very close to Gaussian, with only tight limits on non-Gaussianity, which constrains many exotic inflationary scenarios. The universe appears to have started with simple randomness, not complicated spikes. There is also the possibility of primordial gravitational waves, which would be tensor fluctuations in the metric itself, rather than density variations in matter. If strong enough, they would leave a distinctive B-mode polarization pattern in the CMB, a subtle, swirling signature that cannot be produced easily by ordinary density perturbations. This is a high-stakes prediction because it probes the energy scale of inflation directly, turning a faint polarization pattern into a thermometer for the earliest moments. It is one of the few observational windows into inflation's raw power. So far, B-mode searches have produced upper limits rather than a definitive detection, and those limits already rule out some simple inflation models with large tensor amplitudes. Foregrounds complicate the search because dust in our own galaxy can mimic polarization patterns, and separating signals requires careful multi-frequency observations. The absence of a detection is not a failure of the idea, but it is a constraint that narrows the landscape. It reminds us that inflation is a framework under pressure from data, not a free story. So the evidence for inflation is broad but not singular, and that distinction matters for intellectual honesty. The CMB anisotropy spectrum matches inflation-inspired initial conditions remarkably well, and it does so across many multipoles, not just one favoured scale. The spectral tilt, Gaussianity, and acoustic peak structure align with the inflationary framework, even as the most dramatic signature remains elusive. Inflation looks less like a guess and more like a coherent explanatory package. Large-scale structure surveys extend the same story, because the distribution of galaxies reflects the same primordial power spectrum after gravitational evolution. The cosmic web's filaments and voids are the grown-up version of the same initial ripples, shaped by dark matter's gravitational scaffolding. Baryon acoustic oscillations provide a standard ruler that cross-checks the CMB-based cosmological model, tying early and late epochs together. When different epochs agree, the case becomes harder to dismiss as coincidence. Yet we should keep the logic honest, because cosmology is not a laboratory where we can rerun initial conditions and test alternate histories directly. Inflation is not proven like a tabletop law, and it is not confirmed by a single decisive experiment that closes the case. It is supported because it solves multiple problems at once and predicts patterns that match precision data, often with few adjustable assumptions at the level of broad features. The support is strong, but it is not the same as finality. That support still leaves open questions that shape the mystery, and the first is embarrassingly basic. We do not know what the inflaton is in particle physics terms, and that gap is not a minor technicality. We do not know whether it is a new fundamental field, a known field in an exotic state, or an effective description of deeper dynamics that we have not yet named. The mechanism works on paper, but the actor remains off stage. We also do not know how inflation started, and that question has sharp edges because it touches initial conditions again. Did it require special initial conditions, or is it generic in some deeper theory of high-energy physics and gravity? Some models suggest inflation is hard to begin without already having a smooth patch, which sounds like the original problem returning in a new form. Others argue that inflation can be an attractor, but the debate is ongoing and technical. We also do not fully know how inflation ends in detail, even if the broad picture is clear and reheating is required. Reheating must produce the observed matter content and the enormous entropy of the visible universe, and it must do so without leaving contradictions. The microphysics of that conversion depends on couplings we have not measured, and those couplings determine what particles are produced and how quickly the universe thermalizes. In a sense, reheating is where inflation meets particle physics most directly. There is also the question of uniqueness, because inflation is a framework with many implementations, not a single model with fixed parameters. Alternatives exist, including bouncing cosmologies and varying speed of light ideas, though they face their own challenges and must reproduce the same detailed CMB features. The existence of alternatives forces a careful question: which features of the data truly demand inflation, and which merely accommodate it? The answer is not a slogan, it is a research program. Some inflation models imply eternal inflation, where inflation never ends globally and continues in parts of the larger spacetime. In that picture, our observable universe is one bubble among many regions, each potentially with different low-energy physics after inflation ends locally. That possibility raises new questions about predictability, about what counts as an explanation, and about whether probability itself becomes part of cosmology. It also changes the emotional tone of the story, because our universe becomes one outcome among many. Even without eternal inflation, the framework shifts our view of the central paradox in a way that matters for the theme of this series. Inflation is extreme expansion with no outside space required, because it is the scale factor changing within spacetime, not a fireball pushing into emptiness. It is not an explosion with an edge you could approach, and it is not a balloon inflating into a surrounding room. The geometry is the room, and the room is what changes. But inflation also forces us to talk about vacuum-like energy as a physical driver, and that is where the word nothing starts to wobble. It says that something resembling empty space can dominate the universe's dynamics, and it can do so with measurable consequences written into the CMB. That brings us back to the word nothing, now with sharper physics attached and less room for metaphor. If the vacuum can push spacetime apart, then emptiness is not inert. If vacuum-like energy can inflate spacetime, then empty becomes a misleading adjective, because the vacuum in modern physics is a state with fields, fluctuations, and measurable effects. Even when it looks empty to our senses, it can carry energy, pressure, and quantum uncertainty, and those properties can gravitate. The unsettling thought is that nothing may be a structured medium, and structure can act, sometimes with universe-shaping force. What we call absence may be a kind of presence with rules. So we end this chapter with a pivot, because inflation explains how the universe learned to grow fast enough to look smooth and flat, while also planting the seeds of everything that later formed. It reframes the CMB's uniformity as inherited, the universe's flatness as stretched, and the missing relics as diluted. It also leaves us with a driver that sounds like emptiness but behaves like an engine. The story becomes less about an explosion and more about a state of space itself. Now we follow its engine, vacuum-like energy, into the deeper question of what empty space really is, because that is where inflation points when you ask what powered it. The universe is not expanding into nothing, but inflation makes nothing feel crowded with fields, with potential energy, and with quantum uncertainty. The next chapter enters the quantum vacuum, where absence becomes a kind of presence, and where origins become a question about fields, geometry, and the limits of time. We keep asking what the universe expands into, and the word nothing keeps appearing in the answer. In earlier chapters, expansion became geometry, an evolving metric, rather than debris moving outward through a pre-existing container. Now the paradox tightens, because inflation points to vacuum-like energy as an engine, and that engine seems to live inside emptiness. If emptiness can drive expansion, then emptiness needs a definition that physics can actually use. Begin with the first layer of nothing, because everyday language sets the trap. In ordinary speech, nothing means empty space, a region with no air, dust, or light, like a vacuum chamber after the pump shuts off. Visually, it looks like a dark room with the furniture removed, and it feels like the simplest kind of absence. Classical physics can treat that region as a stage that remains when actors leave, and the stage has coordinates even when no one stands there. In that picture, emptiness has properties like volume and duration, even without matter, because space and time remain as a fixed background. Even the silence has a frame, and the frame is doing work. That first layer is already something, although we rarely admit it out loud. It still has geometry, it still allows rulers and clocks, and it still offers a place for equations to live. Newton's absolute space and time made that intuition feel natural, because the arena was assumed to exist independently of what happened inside it. Even after Einstein, the habit persists, because our brains like containers and contents. When we say nothing, we often mean no stuff, while quietly keeping the stage. The stage may be invisible, yet it is still a structure with measurable relationships. The second layer is the quantum vacuum, and it is not a simple absence at all. Modern physics describes nature with fields, not just particles as tiny billiard balls, and fields are present even when particles are not. An electron is an excitation of an electron field, and light is an excitation of the electromagnetic field, like ripples travelling through a medium that is not made of matter. Even when no particles are present, the fields still exist as the underlying degrees of freedom, and the vacuum is the lowest energy state of those fields. It is not their disappearance, and it is not a blank setting with the lights turned off. In a sense, it is the system at rest. Yet quantum rest is never perfectly still. Historically, this shift from particles to fields was not a mere change of vocabulary. Maxwell's equations already hinted that electromagnetism behaves like a field-filling space, because waves propagate without needing material carriers. Later, the quantum revolution forced a deeper rewrite, because quantizing fields explained how particles can be created and destroyed, while the underlying field remains. The success of quantum electrodynamics made the field viewpoint unavoidable, because it predicted phenomena to astonishing precision. The vacuum became a state of a system, not the absence of a system, and that distinction is crucial. In quantum theory, empty means in the ground state, and ground states can still be active in subtle ways. The quietest possible state still contains the imprint of the rules. The third layer is the hardest, and it is where language begins to fail. Nothing can also mean the absence of spacetime itself. No distances, no durations, no geometry to measure, and no time intervals to count. That is not empty space, because empty space already assumes geometry, and geometry is exactly what is missing here. It is not the quantum vacuum either, because quantum fields are defined on a spacetime background in standard formulations, and the background is part of the definition. When spacetime is missing, even the word where loses its meaning, because where presupposes a map. The question becomes not what fills space, but what space even is. These layers sound similar in everyday speech, but they are different physical claims, and the differences matter. The central question hides an assumption, because asking what expansion is expanding into assumes there is a background arena. General relativity removed that arena by making spacetime dynamical, and it replaced the stage with a participant in the drama. Quantum theory then complicates emptiness by filling the vacuum with structure, correlations, and measurable effects. The paradox is not solved by wordplay, but by tracking which layer we mean at each step. Once the layers are separated, the mystery becomes sharper rather than smaller. To see why the quantum vacuum is not quiet, start with a simple rule that is easy to state and difficult to fully internalize. In quantum mechanics, certain pairs of quantities cannot both be pinned down exactly, even in principle, because the state itself does not allow it. The uncertainty principle is not about sloppy measurement, and it is not a limitation of our instruments, because it arises from the mathematics of non-commuting operators. For a field, the vacuum cannot have both exactly zero field value and exactly zero rate of change everywhere, because that would violate the quantum constraints. The lowest energy state still contains fluctuations, and those fluctuations are built into the definition of lowest. Even if the average is zero, the variance refuses to vanish. A useful image is a perfectly calm lake that cannot be made perfectly still even when the wind stops. The surface is not being disturbed by an external hand, yet it still shows tiny ripples because the rules forbid absolute rest. In quantum field theory, those ripples appear as vacuum fluctuations, and they show up as correlations between field values at different points. The vacuum is not a featureless void, because it has a statistical texture, and that texture can be probed. If you could visualize it, you would see a faint restless grain, subtle but persistent. These fluctuations are often described as virtual particles popping in and out of existence, and the phrase is memorable for a reason. Yet the phrase can mislead, because it suggests little objects briefly appear as if the vacuum were a particle factory. The safer statement is that vacuum expectation values are not perfectly still, and the vacuum state has non-trivial correlations that influence interactions. In many calculations, virtual particles are bookkeeping devices in perturbation theory, and the deeper reality is the field's quantum structure. The effect is not a philosophical preference, because experiments can detect it in controlled settings. The vacuum leaves fingerprints, even when it looks empty to the eye. The Casimir effect is the accessible example that keeps the story grounded, because it turns the vacuum into a measurable force. Place two neutral conducting plates very close together in a vacuum, aligned like two mirrors facing each other across a narrow gap. The allowed electromagnetic modes between the plates differ from the modes outside, because the boundary conditions restrict which wavelengths can fit. That difference changes the vacuum energy density between the plates relative to the outside region. The result is a measurable force that pushes the plates together, and it grows stronger as the plates move closer. In the lab, the distances can be micrometers or less, small enough that quantum structure becomes mechanical pressure. In a visual sequence, the space between the plates looks like a corridor where only certain standing waves are permitted, while outside the corridor the full spectrum of modes can exist. The vacuum, in this view, is not nothing, but a sea of possible oscillations, and the plates edit the sea by imposing constraints. Imagine the plates as strict gatekeepers, allowing only select wave patterns to exist in the narrow slot. The force is small, but it is real, and it has been measured with increasing precision using microfabricated devices. The Casimir effect reveals that the vacuum responds to geometry, and it behaves as though it has physical content. The emptier space becomes sensitive to shape, an eerie kind of responsiveness. Other vacuum effects exist, and they reinforce the same message from different angles. The Lamb shift shows that atomic energy levels shift due to interactions with vacuum fluctuations, and the shift was historically important because it forced refinements in quantum electrodynamics. Spontaneous emission can be described as an excited atom coupling to vacuum modes, as if the vacuum provides the channels into which the atom can radiate. Even the stability of matter relies on quantum rules that prevent electrons from collapsing into the nucleus, and those rules are tied to the quantum structure of fields. The vacuum is a state with rules, not a blank backdrop waiting to be filled. It is less like emptiness, and more like the lowest rung of an intricate ladder. At this point, it helps to pause and ask what we mean by energy in the vacuum, because the word itself can be slippery. In classical mechanics, energy is often a number you assign to objects, like kinetic energy of a moving mass. In quantum field theory, energy is tied to oscillators at every point in space, and each mode behaves like a harmonic oscillator with a ground state energy. Even when the oscillator is in its lowest state, it does not have zero energy, and that leftover is the 0-point contribution. The vacuum, therefore, carries an energy density associated with the ground state of all fields. The strange part is that the baseline is not truly zero. Nature keeps a residual hum. Now connect vacuum to gravity, because gravity responds to energy. In general relativity, energy density and pressure both curve spacetime, and the equations do not give matter a monopoly on influence. The stress-energy tensor includes not only mass and radiation, but also pressures and stresses, and those can be just as important in cosmology. If the vacuum has an energy density associated with its ground state, then it should gravitate, even if no particles are flying around. Empty space can weigh, in the sense that it can influence geometry and change how distances evolve. The vacuum becomes a source term, not a philosophical aside. This connection is not a modern add-on, because Einstein himself introduced the cosmological constant as a term that behaves like a uniform energy density. Historically, it entered the equations as a way to permit a static universe, and later it was abandoned when cosmic expansion became undeniable. Yet the term never truly left the mathematics, and modern observations brought it back with new meaning. In cosmology, vacuum energy appears as the cosmological constant term, and it behaves like a component that does not dilute as space expands. Matter thins out as the universe grows because the same particles occupy a larger volume, and radiation thins out even faster because photons redshift. Vacuum energy, in the simplest model, stays constant per unit volume, as if new vacuum energy appears with new space. Its pressure is negative, and that negative pressure can drive accelerated expansion. The universe can speed up without any engine pushing from outside. The sign logic is subtle but central, and it is worth lingering on because it feels counterintuitive. In the Friedmann equations, the acceleration of the scale factor depends on energy density plus 3 times the pressure, and pressure counts as a source. For ordinary matter, pressure is small compared to energy density, and gravity is attractive, slowing expansion. For radiation, pressure is positive, and it still contributes to attraction. For vacuum energy, pressure is negative and equal in magnitude to the energy density, and that combination flips the sign, producing repulsive gravity in the cosmological sense. The vacuum does not push like a gas in a box, but it changes the geometry's evolution. It is repulsion written into curvature, an effect of bookkeeping in spacetime itself. This is where the tone should stay mysterious, because the numbers do not behave politely. Naive quantum field theory estimates of vacuum energy are enormous compared to what cosmology observes, and the gap is not a small embarrassment. If you add up zero-point energies of known fields up to a reasonable high-energy cutoff, the result can overshoot the observed value by many orders of magnitude. Yet the observed acceleration today corresponds to a tiny effective vacuum energy density, so small that it only dominates after billions of years of cosmic dilution of matter. The mismatch is the cosmological constant problem, and it is one of the deepest unsolved tensions in theoretical physics. The vacuum looks like it should be thunder, yet the universe hears only a whisper. The vacuum is powerful enough to shape the universe, yet it seems almost cancelled, as if nature is balancing a ledger with extreme precision. That cancellation, if it exists, would have to be extraordinarily exact, and it would need to persist across cosmic history. Why should the vacuum's energy nearly vanish, while not vanishing completely? And why should it take the particular value that becomes important precisely in the era when galaxies and observers exist? The question is scientific, but it also feels like a riddle written into the equations. When the universe accelerates so late, it tempts us to ask what sets the timing. So we have two truths that do not sit comfortably together, and the discomfort is productive. Quantum theory suggests vacuum energy should be huge, because every field has zero-point contributions and those contributions add. Cosmology suggests the effective value is small, because the universe accelerates gently, not violently, and structure had time to form. Something about our accounting is incomplete, or our understanding of gravity is missing a piece, or both. Every answer opens a deeper question, and the vacuum becomes a clue rather than a conclusion. The emptiest concept in language becomes one of the heaviest in mathematics. Now return to origins, because the word nothing is often used as a beginning, and beginnings invite metaphors. People ask whether the universe came from nothing, as if nothing were an empty room waiting to be occupied. But empty room is the first layer, and it already assumes spacetime exists with walls made of geometry. Quantum vacuum is the second layer, and it assumes fields and laws exist, along with a stage on which fields are defined. Absence of spacetime is the third layer, and it challenges what laws even mean, because laws are usually written in terms of time, space, and change. The deeper the nothing, the more the question becomes about assumptions we cannot see. Universe origin proposals live inside these layers, and each proposal makes assumptions that are easy to miss if we only hear the headline. None is a settled fact, and each is a hypothesis framed by incomplete physics, because we do not yet have a confirmed theory of quantum gravity. The goal is not to declare a winner, but to clarify what each model claims, what it takes as given, and what it tries to explain. We track what is assumed about spacetime, time, and the laws, because assumptions are the hidden scaffolding of every origin story. When the scaffolding changes, the meaning of beginning changes with it. One class of ideas uses quantum tunneling from nothing, and the phrase is deliberately provocative. In these proposals, a universe can nucleate as a quantum event, like a particle appearing on the other side of a barrier without climbing over it. The word nothing here usually means no classical spacetime, not an empty region within spacetime, and that distinction is the point. The tunneling is described by a quantum amplitude for a small closed universe to appear, often with a specific geometry like a tiny three-sphere. The laws of quantum gravity are assumed to exist, even if spacetime does not, and that assumption carries weight. The event is not located in time, because time is part of what is being born. This sounds like creation ex nihilo, but it is not creation without structure, because the mathematics is doing real work. It relies on a framework that assigns probabilities to geometries, and it relies on boundary conditions that define what counts as nothing in the first place. In a visual metaphor, it is less like a universe appearing in an empty room, and more like a bubble forming in a landscape of possible configurations. The mystery shifts from material origin to the origin of the rulebook, because the rulebook is already there, quietly presupposed. If the rulebook is timeless, what does it mean for it to exist at all? If laws exist to allow tunneling, in what sense was there nothing, and what does it mean for laws to exist without time? Is the nothing a physical state, or a boundary condition in a mathematical description, or a limit of a path integral? The questions do not invalidate the idea, but they clarify what the idea is actually claiming. The universe may emerge from a minimal structure, yet minimal is not the same as non-existent. The word nothing keeps shrinking, yet it never quite reaches zero. Another proposal is the Hartle, hawking no-boundary idea, and it aims to remove the sharp edge of a beginning. It suggests the universe has no initial boundary in time, in the same way a sphere has no edge on its surface, even though it is finite. Near what we call the beginning, time behaves like a spatial dimension in a Euclideanized geometry, and the distinction between time and space becomes blurred. The universe is finite but unbounded in this extended sense, so the beginning is not a singular moment with an infinite density. The model tries to replace an abrupt boundary condition with a smooth geometric cap. Visually, the timeline softens into a rounded surface. No corner, no tear. No boundary is often summarized as no before, but the careful version is subtler and more technical. It reframes the earliest region so that the classical notion of time does not apply, and it treats the early universe as a region where the usual temporal ordering is not fundamental. It still uses a path integral over geometries, which assumes a quantum gravitational framework and a notion of how to weigh different histories. It also raises interpretive questions about what counts as physical time, because time becomes an emergent parameter that appears only in certain regimes. The price of removing an edge is changing what time means at the start. The beginning becomes a change of signature rather than a bang. A third family of ideas replaces a beginning with a bounce, and the imagery is almost cinematic. In bounce models, the universe contracts, reaches a high-density regime, then expands again, turning the Big Bang into a transition rather than an origin. The bounce can be driven by quantum gravity effects, exotic matter components, or modified gravity depending on the model's details. Cyclic scenarios extend this into repeated phases, sometimes with branes or extra dimensions in the background, and the universe becomes a sequence of epochs rather than a single arc. These models aim to avoid a singularity by turning it into a passage. The spotlight shifts from creation to continuity, how the story crosses the narrowest point. Bounces also come with assumptions that must be stated clearly, because avoiding a singularity is not free. They require a mechanism that prevents collapse into a singularity and preserves a sensible notion of time through the bounce, so that before and after remain meaningful. They must address entropy growth, because cycles can accumulate disorder, and a truly cyclic universe must explain why the cycles do not run down. They must also reproduce the observed near-scale invariant perturbations, which inflation explains efficiently with quantum fluctuations stretched to cosmic scales. A bounce can move the mystery, but it does not automatically remove it. If the universe had a prior phase, what preserved its information, and what erased its scars? At this point, the question of before the Big Bang becomes a test of language, and language can fail quietly. In general relativity, time is part of spacetime, not an external parameter ticking in the background like a universal metronome. If spacetime begins, then time begins with it, at least in the classical description, because there is no time coordinate outside the manifold. Asking what happened before can become like asking what is north of the North Pole, because the grammar works while the coordinate does not. The question feels meaningful, yet it may not map onto the structure of the theory. Our intuition keeps reaching for a calendar, even when the calendar is part of the object. This does not mean the question is meaningless in every theory, and that nuance matters. It means the question depends on what replaces classical spacetime at the earlier stage, and different proposals answer in different ways. If a bounce occurs, there is a before in the sense of an earlier phase with its own time direction. If no boundary is right, before is not a valid temporal direction near the start because time behaves like space in that regime. If tunneling is right, the notion of time may emerge only after nucleation, and the event is described without a prior temporal sequence. The same word can point to different structures, depending on the theory behind it. The word before is not universal, because time may not be fundamental, and that is a profound shift. We're used to time as the background in which all stories unfold, including scientific stories, and we build causality around it. Yet in quantum gravity, time can become a derived concept, an approximation that works when spacetime is smooth and classical. If time is emergent, then origin questions must be asked with new grammar, and that is part of why the topic remains unsettled. What would it mean to explain a beginning without using time as the explanatory scaffold? Now revisit the singularity, because it is the cliff edge in the classical story, and it is where our confidence breaks. In Chapter 3, we treated the singularity as a sign of geodesic incompleteness, meaning there are paths in spacetime that cannot be extended smoothly. It is not necessarily a physical point where infinity literally exists, but a breakdown of the smooth metric approximation that general relativity relies on. The Planck epoch marks where quantum gravity should dominate, around 10^43 seconds after the putative beginning, when energies and curvatures reach scales where quantum effects of spacetime itself cannot be ignored. In that regime, our current theories are incomplete and our equations stop being trustworthy guides. The map ends, not necessarily because the territory ends, but because the ink runs out. Quantum gravity is expected to change the rules, but we do not yet have a confirmed theory, and that absence shapes every origin proposal. Candidates include string theory, loop quantum gravity, and other approaches that treat spacetime as emergent or quantized, sometimes replacing the continuum with discrete elements. They often predict that classical singularities are resolved, replaced by new phases, quantum bounces, or microscopic structures that prevent infinite curvature. Yet none has delivered a single, testable, universally accepted account of the beginning, and the lack of decisive observational access makes the problem harder. The absence of a complete theory is part of the story's tension, because the vacuum and the beginning both live at the edge of our knowledge. We can write equations, but we cannot yet check the earliest pages. Even without a final theory, we can state what we expect, because expectations come from the way quantum theory behaves in every other domain. At Planck scales, quantum fluctuations of geometry should be significant, and the metric itself may have uncertainty, so distance and duration become fuzzy concepts. The idea of a smooth spacetime manifold may fail, replaced by a microscopic weave, a network, or a different mathematical object that approximates smoothness only at large scales. In that picture, the beginning is not a moment in time, but a question about what spacetime is made of, and how classical time emerges. The origin becomes a materials science problem, except the material is geometry. This loops back to the central question in a sharper form, because it reframes expansion and emptiness together. The universe does not need an outside space to expand into, because expansion is the evolution of spacetime geometry from within, and the geometry is the thing that grows. But if geometry is dynamical, it can also have a ground state, fluctuations and energy, just like other physical systems. The vacuum is not an empty container, it is a physical state of fields and possibly of spacetime itself, and that state can influence cosmic history. Nothing becomes a layered concept, not a single void, and each layer carries different physics. The more carefully we define nothing, the more it starts to look like a spectrum of possibilities. Now connect vacuum energy to inflation, because inflation is our recent narrative engine, and it makes the vacuum operational. Inflation used a vacuum-like state with negative pressure to drive rapid expansion, stretching tiny regions to cosmic scales in a fraction of a second. That state may be a high-energy vacuum of a field, or a metastable configuration that later decays, releasing energy into particles and radiation. Quantum fluctuations in that state were stretched outward, becoming the seeds of structure, and the cosmic microwave background kept the receipts in its temperature pattern. Inflation therefore treats the vacuum as a working component of the universe, not a philosophical placeholder. It turns the vacuum into a mechanism you can model, constrain, and compare with data. In visuals, the inflationary vacuum is often shown as a smooth, almost featureless field value across space, with faint quantum noise riding on top. As expansion races ahead, those faint ripples are pulled beyond the horizon, freezing into classical-looking perturbations that later re-enter and grow into galaxies. The story is elegant, but it also deepens the mystery, because it ties the largest structures to the smallest fluctuations. If the vacuum can do that, then nothing is not passive, and it cannot be dismissed as mere absence. The universe's grand architecture may be the amplified echo of microscopic uncertainty. This sets up the present-day question, because the universe appears to be accelerating again, and the echo is hard to ignore. The acceleration is far gentler than inflation, but the sign is the same, and the equations point to a component with negative pressure dominating the expansion today. The simplest label is dark energy, and the simplest model is a cosmological constant, which behaves like vacuum energy. If dark energy is vacuum energy, then the vacuum is still shaping cosmic history, from the earliest fractions of a second to the fate of the far future. The early universe and the late universe may be linked by the physics of emptiness, even if the link is not yet understood. The same concept returns at two cosmic extremes, beginning and end, but the link is not yet understood, and that is where we build toward the climax, because the questions sharpen rather than fade. If vacuum energy drove inflation, why is the current vacuum energy so small? And why did it not dominate earlier and prevent structure? If the vacuum is a quantum ground state, why does it not gravitate catastrophically, given what naive calculations suggest? If the cosmological constant is a parameter, why does it take the value it does, and why does it appear so finely balanced? The universe seems to balance on a number that should not be stable, and stability without explanation feels like a clue. Are we missing a symmetry, a cancellation, or a new principle hiding in plain sight? We also confront a deeper unease that sits beneath the equations, because every origin proposal assumes some framework of laws, even when it claims to start from nothing. Tunneling assumes a quantum rulebook that assigns amplitudes to geometries, and it assumes a notion of what counts as a boundary condition. No boundary assumes a path integral and a notion of analytic continuation, and it assumes that such mathematical operations correspond to physical meaning. Bounces assume a mechanism that violates classical energy conditions or modifies gravity, and they assume that the modification is consistent and stable. The question shifts from where the universe came from to why there are laws that allow a universe at all, and that shift is part of the chapter's mood. The deepest nothing may not be emptiness, but the absence of explanation. So we end this section by tightening the mystery rather than resolving it, because resolution would be dishonest. Nothing is not empty space, because empty space already has space-time, and space-time is a kind of structure. Nothing is not the quantum vacuum, because the vacuum is a structured state of fields with measurable effects, and experiments can feel its presence. Nothing as absence of space-time is a deeper claim, and our physics there is incomplete because we lack a confirmed quantum theory of geometry. When we ask how the universe began, we're also asking what nothing could possibly mean, and whether the word can survive contact with the equations. The more precise we become, the more the word resists us. This brings us to the next crucial distinction, because the present expansion is no longer slowing down. If a vacuum-like component is accelerating the universe today, then the word nothing is not only about origins, and it is not only about the first instant. It is about the current fate of space-time and the long-term horizon of what can ever be observed, because acceleration creates horizons that limit causal contact. The same emptiness that might have powered inflation may now be shaping the endgame, quietly determining what remains visible as galaxies drift beyond reach. In the far future, the night sky itself becomes an experiment in what acceleration erases. Now we follow that gentle acceleration into dark energy, where the vacuum becomes a cosmic parameter that can be measured, constrained, and argued over. We ask whether the universe's expansion is being driven by a true cosmological constant, or by a changing field, and we ask how the data can tell the difference. We ask what observations can distinguish them, and what the answer would mean for the idea of nothing, because constant and changing imply different kinds of vacuum. The paradox returns as a measurement problem, and the stakes become the future of spacetime itself. Expansion should slow as gravity gathers matter and pulls on the cosmic fabric, because every clump of mass deepens the surrounding curvature. In the standard intuition, the universe begins with a headlong rush, then gradually loses speed as attraction does its work. Yet the late universe does something stranger, something that reads like a contradiction written into the sky. The scale factor does not merely keep growing, as it would in a coasting cosmos. Its growth rate increases quietly at first, then unmistakably, so that emptiness seems to carry a gentle, persistent push. Visually, it helps to imagine a grid drawn across space, a mesh of faint lines connecting galaxies like points on graph paper. In a decelerating universe, that grid stretches, but the stretching eases with time, as though tension were being relieved. In an accelerating universe, the opposite happens. The grid stretches and then stretches faster, and the spacing between lines widens more quickly the longer you wait. The effect is not explosive in any one moment, yet it is relentless, and it changes what far away means from one era to the next. We return to the central question with sharper stakes, because the discovery of acceleration forces us to recheck our most basic mental pictures. In general relativity, expansion is not motion into an external void, and it is not a blast wave pushing into surrounding emptiness. Expansion is the changing metric that defines distance itself, the rule by which rulers and light signals relate separated events. If the metric's growth accelerates, we are not watching galaxies step on a gas pedal. We are watching spacetime's ruler change its rate of stretching, an evolution of geometry, not a conventional motion through space. That distinction matters because it prevents a category error that is easy to make on screen. A galaxy can be nearly at rest relative to its local spacetime, drifting only with small, peculiar velocities from nearby gravitational pulls. At the same time, the distance to a far galaxy can increase rapidly, because the metric between them is changing. The universe can expand faster than any rocket could travel, without violating local special relativity, because no object is outrunning light in its own neighbourhood. For decades, cosmologists expected deceleration, and the expectation was not casual. Matter attracts, and radiation once dominated even more strongly, because radiation pressure and energy density were both enormous in the hot early universe. In the simplest Friedman models, the early universe should have slowed from its initial rush, like a ball thrown upward that climbs, hesitates, and then begins to fall. The key task was to measure that slowdown directly, using light as a time machine and the universe itself as the laboratory. That measurement is subtle because we cannot watch a single galaxy for billions of years and see it change course. Instead, we look outward and therefore backward, sampling many cosmic times at once. Nearby galaxies show the universe in its recent state, while distant galaxies show it in its younger state, because their light has travelled longer. The question becomes geometric. What is the relationship between redshift and distance, and how does that relationship curve as we look deeper into time? The tool arrived through a special kind of stellar death, one that seems almost engineered for cosmology. Type Ia supernovae explode with remarkable uniformity, producing a brief, intense flash that can rival an entire galaxy. They occur when a white dwarf in a binary system is pushed to instability, often near the Chandrasekhar limit of about 1.4 solar masses. In many scenarios, the white dwarf accretes matter from a companion, or merges with another white dwarf, until the density and temperature ignite runaway carbon fusion. A white dwarf is supported by electron degeneracy pressure, a quantum mechanical effect that resists compression even when the star has exhausted normal nuclear fuel. That support has a limit, and near that limit the star becomes a powder keg. When ignition begins, the burning front races outward, converting carbon and oxygen into heavier elements such as nickel and iron group nuclei. The energy release unbinds the star in seconds, leaving no compact remnant, just an expanding shell of debris, glowing as radioactive isotopes decay. The details vary, and those details matter for precision, because nature rarely gives perfect copies. Some explosions may begin as deflagrations, others may transition to detonations, and the composition of the progenitor can shift the yield. Yet the overall outcome is a bright, fast flare that can be seen across billions of light years, and its spectrum carries recognizable features. In the days after peak brightness, the light curve is powered largely by the decay chain from nickel-56 to cobalt-56 to iron-56, turning nuclear physics into a cosmic beacon. They are not perfect standard candles, but they are standardizable, and that nuance is the heart of their usefulness. Their peak brightness correlates with how quickly they fade, a relationship often called the Phillips relation. Broader light curves mean intrinsically brighter explosions, and narrower curves mean dimmer ones, because the amount of nickel produced influences both luminosity and diffusion time. With careful calibration, each event becomes a distance marker, a candle whose wattage can be inferred rather than assumed. On screen, this becomes a plot that looks deceptively simple. Brightness versus time, a rise to a sharp peak, then a decline that can be stretched or compressed. The curves are aligned, corrected for colour and extinction, and then compared like fingerprints. A supernova that fades slowly is treated as a higher wattage bulb, while a fast-fading one is treated as lower wattage. The calibration turns messy astrophysical explosions into a tool for geometry, which is why it changed cosmology. This method plugs into the distance ladder built earlier, because no single technique spans all scales. Nearby Type Ia events can be calibrated using Cepheids or other geometric anchors, including parallax and Massa distances in select galaxies. That calibration then extends to far redshifts where Cepheids are too faint to resolve as individual stars. The ladder becomes a bridge from local space to deep cosmic time, with each rung checked against the next for consistency. The ladder metaphor is more than tradition, because each rung carries its own systematic risks. Cepheids depend on metallicity corrections and crowding in host galaxies, while supernovae depend on dust, intrinsic scatter, and selection effects. Cosmology advances when these uncertainties are confronted openly, not when they are ignored. The 1990s supernova work succeeded because it treated systematics as central characters, not as footnotes. Two teams pushed this approach to its limit in the 1990s, at a moment when detectors and computing finally made the search practical. The Supernova Cosmology Project and the High-Z Supernova Search Team hunted distant type IR supernovae by repeatedly imaging the same patches of sky. They used difference imaging, subtracting earlier exposures from later ones to reveal new points of light blooming in remote galaxies. They built samples large enough to compare brightness against redshift with statistical confidence, and they did it under the pressure of time, weather, and telescope schedules. Their goal was straightforward in phrasing, yet profound in implication. Measure the deceleration parameter and weigh the universe's gravity, because gravity should leave a signature in the Hubble diagram. In a matter-dominated universe, distant supernovae should appear brighter than in a coasting model, because the expansion would have been faster in the past and then slowed. The curve of distance versus redshift would bend in a specific direction, and the data would reveal how strongly the universe had been braking. The result landed like a quiet shock. Distant supernovae were dimmer than expected in a decelerating universe. Dimmer means farther away at the same redshift, because the light is spread over a larger area by the time it reaches us. Farther means the universe expanded more than gravity alone would allow, as though the braking had weakened and then reversed. The simplest reading was that expansion has been speeding up for several billion years, beginning after the universe had already formed galaxies and large-scale structure. In a visual sequence, the Hubble diagram becomes a suspense plot. Points appear with error bars, first scattered, then settling into a trend, and then drifting away from the decelerating prediction line. The divergence is not dramatic like a cliff, yet it is persistent across redshift, and it survives improved calibration. The universe, it seems, is not merely expanding, it is accelerating. This is where a common misconception must be cut off cleanly, because the wrong picture spreads faster than the right one. Accelerated expansion does not mean galaxies are accelerating through space like rockets, nor does it mean the Milky Way is being pushed by a force in the usual sense. Most galaxies sit nearly at rest in co-moving coordinates, carried by the metric, while their local motions remain governed by nearby gravity. The acceleration is in the scale factor AT, not in a local velocity field that could be measured with a speedometer. In cosmology, we track how AT changes with time, and we do it with equations that tie geometry to energy content. The Hubble parameter h is the fractional growth rate of the scale factor, defined as h pre 1a dt, which is why it has units of inverse time. Acceleration means the time derivative of h is not the headline, because h can decrease even in an accelerating universe. The headline is that the second derivative of at is positive, so distances between co-moving points grow faster and faster, even if each point feels locally inertial. This distinction can sound technical, but there is a plain language translation. The universe can be expanding, and the expansion rate can be changing, and those are separate statements. A car can move forward while its speed changes, and the sign of acceleration tells you whether it is speeding up or slowing down. In the cosmos, the speed is the scale factor's growth, and the acceleration is how that growth itself evolves. The redshift of light still functions as the receipt, because photons stretch with the metric as they travel. Redshift encodes the ratio of scale factors between emission and observation, so a higher redshift means the universe has expanded more since the light left. Brightness adds another receipt, because flux falls with distance and with redshift effects on photon energy and arrival rate. Put together, redshift and brightness trace the expansion history, turning supernovae into time-stamped markers on the universe's growth curve. There is also a geometric subtlety hiding in the brightness calculation, and it becomes important when precision tightens. In an expanding universe, the luminosity distance differs from simple Euclidean distance, because the surface over which light spreads is affected by curvature and by the changing scale factor. Each photon is redshifted, reducing its energy, and the arrival rate of photons is time-dilated, reducing the flux again. These factors combine so that the observed dimness carries the imprint of spacetime dynamics, not merely the imprint of how far. A subtlety matters for credibility, because extraordinary claims in cosmology often die by ordinary astrophysics. Supernova dimness could be faked by dust, evolution, or selection bias, and critics raised each possibility immediately. Dust can absorb light, and if it were grey enough, it could dim without reddening, mimicking distance. Supernova populations might evolve with cosmic time, changing intrinsic brightness. Surveys might preferentially detect brighter events at high redshift, skewing the sample in complicated ways. Teams tested grey dust models, host galaxy correlations, and light curve systematics, because the signal had to survive every plausible alternative. They compared colours, spectra, and populations across redshift, looking for telltale shifts in absorption features or in the distribution of light curve shapes. They also examined where supernovae occurred, because host galaxy type and local star formation can correlate with supernova properties. The acceleration signal survived, then strengthened as datasets grew, and later surveys improved infrared observations where dust effects are reduced. Independent probes joined the case, and their value was philosophical as much as statistical. Baryon acoustic oscillations provided a standard ruler in galaxy clustering, a fossil imprint of sound waves in the early plasma. The CMB fixed early universe parameters and the sound horizon scale, anchoring the model at a time when the universe was only about 380,000 years old. Weak lensing and cluster counts added growth of structure constraints, sensitive to how fast matter clumps under gravity. Different methods converged on the same conclusion. A new component dominates the cosmic energy budget today. The convergence matters because these probes are vulnerable to different errors. Supernovae measure relative distances through brightness, while BAO measures a preferred separation scale through clustering statistics. The CMB measures anisotropies in temperature and polarization, which encode geometry, composition, and initial conditions. When these independent lines intersect in parameter space, the intersection is hard to dismiss as a shared illusion. The universe is telling the same story in multiple dialects. We name that component dark energy because we do not know its identity, and the name is a placeholder, not an explanation. Dark here means not directly luminous and not directly detected as particles in a laboratory. Energy is a reminder that it enters the equations as a form of stress energy that shapes curvature. What we do know is its effective behavior in the Friedmann equations, which govern the scale factor in homogeneous and isotropic models. It acts like a smoothly distributed energy density with strongly negative pressure. General relativity tells us why pressure matters, and this is one of its most counterintuitive lessons. In Newtonian gravity, only mass density sources gravitational attraction, and pressure is a side detail. In Einstein's theory, pressure contributes to gravity because it is part of the stress-energy tensor, and gravity responds to the full package of energy, momentum, and stress. The acceleration equation depends on energy density plus 3 times pressure, a combination that determines whether expansion decelerates or accelerates. For normal matter, pressure is small compared with energy density, so the combination stays positive and expansion decelerates. For radiation, pressure is positive and equals 1/3 of the energy density, so the combination stays even more positive and deceleration is stronger. For a component with sufficiently negative pressure, the combination can become negative and the scale factor accelerates. The plain language translation is stark. If the universe is filled with something whose pressure pulls outward in the equations, gravity can become effectively repulsive on large scales. The simplest candidate is the cosmological constant, L, a term Einstein originally introduced and later regretted, though history has complicated that regret. It behaves like a constant vacuum energy density filling space uniformly, the same everywhere and everywhen in the simplest model. Its equation of state parameter W equals -1, meaning its pressure is negative and equal in magnitude to its energy density. As space expands, matter dilutes and radiation redshifts away, but L does not thin out, so it eventually dominates. This feature sounds like creation from nothing, and it tempts the wrong picture, so the narration must slow here. If vacuum energy density stays constant while volume grows, the total vacuum energy in a comoving region increases, which feels like energy appearing as the universe expands. In everyday accounting, that feels impossible, because we are trained to expect a global conservation law. In general relativity, global energy conservation is not defined the same way in an expanding spacetime, because the metric itself changes and the bookkeeping is geometric, not Newtonian. A more careful statement is that local conservation still holds, encoded in the vanishing divergence of the stress-energy tensor. Energy and momentum are conserved locally, in the sense that what flows out of a small region must be accounted for by changes inside it. But the universe as a whole is not a closed box with a fixed notion of total energy, because the box is the space-time geometry. When the geometry evolves, the concept of a single global energy number becomes ambiguous, and that ambiguity is not a loophole. It is part of what expansion means. A cosmological constant also fits the data with brutal efficiency, which is both satisfying and unsettling. A flat LCDM model matches CMB anisotropies, BAO distances, and supernova luminosity distances with a small parameter set, and its predictions have held up through increasingly precise surveys. It predicts a late transition from matter domination to dark energy domination, so that structure forms first and acceleration arrives later. It explains why acceleration begins relatively recently, after galaxies and clusters had time to assemble. Recently, in cosmology, still means billions of years, and the timing has a peculiar resonance. If L is truly constant, then its density was always there, but it was irrelevant when matter density was high. Only when the universe expanded enough for matter to dilute did L take over, like a background note that becomes audible only when the orchestra quiets. That coincidence raises a question that is hard to ignore. Why should we live near the era when the densities are comparable, rather than in a time when one term completely dominates? But L is not the only option, and the alternatives clarify what we are actually measuring, because observations constrain behavior more directly than identity. One alternative is quintessence, a slowly evolving scalar field that permeates space, somewhat analogous in form to fields used in particle physics. Its energy density changes with time, and its W can differ from -1, typically staying above -1 in many models. If W varies, the expansion history changes subtly, and so does the growth rate of cosmic structure. Quintessence keeps the vacuum-like idea but makes it dynamic, which shifts the mystery rather than removing it. The field rolls on a potential, and its kinetic and potential energies set its pressure, much as a ball rolling on a landscape trades potential energy for motion. If potential energy dominates, U stays near -1 and acceleration occurs, because the field behaves almost like a cosmological constant. If kinetic energy becomes important, W rises and acceleration weakens, and the universe's future becomes less rigidly fixed. Observations therefore become a search for time variation in W, and this is where precision cosmology turns into detective work. Supernovae constrain the distance-redshift relation, BAO constrains the ruler scale at different epochs, and lensing constrains how quickly matter responds. If W differs from -1 by even a few percent, the differences accumulate across billions of years, and the curves shift. The challenge is that astrophysical noise and calibration uncertainties can mimic small shifts, so the evidence must be cross-checked across methods. Another alternative is modified gravity, and it is conceptually distinct even if the data can look similar. Perhaps the stress-energy content is ordinary, but gravity's large-scale behavior differs from general relativity, especially on horizon scales where the theory has been tested less directly. In that case, the same expansion history could be produced without a new energy component, because the link between energy content and geometry would be altered. The key discriminator is not only distances, but structure growth and lensing, because modified gravity often changes how gravitational potentials evolve and how matter clusters. In practical terms, cosmologists ask whether the universe's geometry and the universe's growth agree with the same set of rules. General relativity ties them together tightly, so a measured expansion history predicts a specific rate at which structure should form. If we observe a mismatch, distances implying one story, growth implying another, then the culprit could be gravity itself. That is why surveys map both the positions of galaxies and the subtle distortions of their shapes, because lensing sees the integrated effect of gravity along the line of sight. These options share a narrative point that keeps the chapter honest. Dark energy is inferred from geometry and dynamics, not seen directly as a glowing substance or a detected particle. We measure how light propagates through expanding spacetime, and how matter responds to gravitational potentials that deepen and decay over cosmic time. The inference is strong, but it is still an inference about the metric's evolution, made from the patterns imprinted on photons and galaxies. Now the chapter's tension sharpens into a single number, and it is a number that refuses to fit comfortably in our theories. The observed dark energy density is tiny in particle physics units, roughly 1029 grams per cubic centimetre, or about a few proton masses per cubic metre. In energy terms, it is around 10^3 in natural units, astonishingly small compared with scales familiar from quantum fields. Yet quantum field theory suggests the vacuum should carry enormous zero-point energy, because every field has fluctuations even in its ground state. This is the vacuum catastrophe, also called the cosmological constant problem, and it is not a matter of taste. In quantum field theory, each field mode contributes a ground state energy, like a harmonic oscillator that cannot be perfectly still. Summed up to a high energy cutoff, the vacuum energy density becomes huge, and the sum grows rapidly with the cutoff scale. Even if the cutoff is set far below the Planck scale, the result is still wildly larger than what cosmic acceleration implies. The mismatch is not a minor discrepancy that better measurements will smooth out, because it spans an absurd range of magnitudes. Depending on assumptions, naive estimates overshoot the observed value by tens of orders of magnitude, often quoted as 60 to 120 orders, which is beyond ordinary scientific embarrassment. It is a clash between two frameworks that both work extremely well in their domains, which is why it feels like a signpost rather than a nuisance. Quantum field theory predicts vacuum effects in the lab with extraordinary precision, while general relativity predicts gravitational dynamics with extraordinary precision. When we combine them in cosmology, the simplest combination fails spectacularly, and that failure is informative. It suggests that either vacuum energy does not gravitate the way we think it should, or our accounting of vacuum energy is incomplete, or the way gravity couples to quantum fields changes in curved spacetime. Each possibility points to missing physics at a deep level, because it sits at the intersection of quantum theory, gravity, and the structure of spacetime. The universe is forcing a conversation between theories that usually speak past each other. A second layer of unease follows, and it cuts in the opposite direction. If the vacuum energy were exactly zero, that would also demand explanation, because it would require a perfect cancellation among contributions that have no obvious reason to cancel. Symmetries like supersymmetry could cancel contributions, because bosonic and fermionic modes contribute with opposite signs in certain contexts. But supersymmetry is broken at energies we have tested, and broken symmetry leaves a leftover vacuum energy that should still be far too large. So the universe seems to cancel almost everything, but not quite. And not quite is the most mysterious part. It is as if a cosmic ledger is balanced to an absurd precision, yet a tiny residue remains, just enough to accelerate the expansion today. Is that residue a clue to a mechanism, or a coincidence that demands a selection effect, or a sign that we are missing a principle? The question hangs over every dark energy model, because any successful explanation must address not only what dark energy does, but why its scale is so small. This is where the word nothing becomes dangerous, because language invites the wrong metaphors. The quantum vacuum is not empty, and the cosmological constant behaves like vacuum energy, so empty space becomes an active player. If vacuum energy is real, then emptiness is an ingredient in gravity, not a mere absence of matter. The phrase expanding into nothing becomes the wrong mental model, because expansion is the evolution of spacetime itself, and the vacuum is part of what spacetime is. We can restate the paradox in a more precise form, and precision helps the mystery feel real rather than poetic. The universe does not need an outside container to expand, because the metric provides its own notion of distance. Yet the vacuum inside the universe may set the expansion's acceleration, acting as a term in the equations that grows dominant as matter thins out. The driver is not beyond the cosmos, but woven into the metric and the fields that live on it. Nothing is not an exterior. Nothing is a physical state with measurable consequences. Acceleration also changes what the universe can ever show us, and this is where the story turns from measurement to meaning. In a decelerating universe, more and more regions come into causal contact over time, because the expansion slows and light can gradually catch up. In an accelerating universe, an event horizon can form, creating a boundary in space-time beyond which signals emitted now will never arrive. There are galaxies whose light will never reach us no matter how long we wait, even though they exist within the same overall cosmos. This is not because light is too slow in a local sense, and it is not because the universe breaks special relativity. Locally, light always moves at c, and any observer can measure that speed in their neighborhood. The limit comes from the metric's expansion, which can stretch the space between us, and a distant emitter faster than light can close the gap over the long term. Horizons are global features of spacetime, not local speed limits, and they are defined by the entire future history of expansion. The observable universe becomes a moving boundary, not a physical edge, and the distinction is crucial for clear imagery. The particle horizon marks the farthest distance from which light has reached us since the hot early era, so it is a record of what has already had time to arrive. The event horizon marks the farthest distance from which light emitted now will ever reach us in the future, so it is a statement about what can ever be observed. Acceleration makes the event horizon finite, turning the future into a narrowing funnel of accessible information. That finiteness has emotional weight and scientific consequences because it implies a gradual loss of cosmic context. Over time, more galaxies cross beyond our event horizon, not by moving through space like ships, but by being carried outward by the metric's growth. Their photons become so redshifted and diluted that they fade from detectability, stretched into wavelengths longer than any practical instrument can collect. The cosmic web thins into isolation, and the observable universe shrinks in practical terms, even as space keeps expanding. Imagine the night sky in the far future, when the local group has merged into a single large galaxy, and the rest of the cosmos has dimmed away. The background galaxies that now fill deep field images would be gone, not destroyed, but hidden beyond the horizon's reach. The CMB itself would be redshifted to wavelengths so long that it would be almost impossible to detect against local noise. Cosmology would become harder, not because the universe changed its laws, but because the evidence would have slipped beyond the boundary of observation. Now we look forward, because dark energy is also a story about fate, and fate in cosmology is a matter of equations rather than prophecy. If dark energy is a true cosmological constant, acceleration continues forever, and the scale factor grows roughly exponentially at late times. Matter becomes increasingly dilute, star formation ends as gas is used up or locked away, and the universe approaches heat death. The far future becomes cold, dark, and dominated by horizon-scale emptiness, with isolated gravitationally bound islands separated by expanding darkness. Heat death is not a single event, but a long drift toward maximum entropy, where usable energy gradients fade, stars burn out, stellar remnants cool, and interactions become rare as densities fall. The expansion does not tear apart bound systems in the L case, because local gravity and electromagnetic forces remain dominant at those scales. Instead, the universe becomes quiet, with long time scales and little new structure, while the horizon sets a limit on what can ever be contacted. If dark energy is dynamic, the future can branch, and the branches are defined by how W behaves over time. If W stays near -1 but slowly evolves, acceleration could weaken or strengthen, and the event horizon could shift accordingly. If dark energy decays, expansion might return to matter-like behavior, and distant regions could gradually come back into causal contact. If dark energy grows in density, acceleration can become violent, changing not only what can be seen, but what can remain bound. That violent branch is the Big Rip scenario, and it remains speculative because it requires a specific and currently unsupported equation of state. If W is less than -1, called phantom energy, the dark energy density increases as the universe expands, which is the opposite of ordinary dilution. The scale factor can diverge in finite time, and the approach to that divergence would be marked by a sequence of disruptions. Bound structures could be torn apart in order, from clusters to galaxies to solar systems to planets, and in the most extreme extrapolations, even atoms. We should keep the hierarchy clear, because the narration must not oversell what the data allows. Heat death is the conservative extrapolation of L, and it follows from the simplest model that fits current observations. Big Rip requires a special W and a persistence of that behavior, and current constraints are consistent with W near -1. Other exotic endings exist, including recollapse in certain models, but current data favors continued acceleration. The core point is that the expansion history determines causal structure, and causal structure determines what can exist as an observable fact. This returns us to the documentary's hook about the growing map, and it is worth lingering on the visual logic. The map is not adding new land at the edges, because there is no edge in the usual sense within the model. The scale of the map is changing everywhere at once, so that every distance printed on it becomes outdated as soon as it is written. Dark energy says the scaling itself is changing its pace, as if the paper has a built-in tendency to stretch, slowly at first, then more insistently. We can now connect late-time acceleration to the earlier chapter on the quantum vacuum, because the rhyme is too suggestive to ignore. Inflation was an early episode of accelerated expansion, driven by vacuum-like energy, smoothing and flattening the universe while amplifying quantum fluctuations into cosmic structure. Dark energy is a late episode of accelerated expansion that looks vacuum-like again, though at an energy scale unimaginably smaller. The energy scales are wildly different, but the sign of the effect rhymes, and the rhyme invites the question of whether the universe is repeating a theme. That rhyme could be coincidence, or it could be a clue, and the chapter's tone lives in that uncertainty. Perhaps vacuum energy is real and small for a deep reason we do not yet understand, a reason that links quantum fields to space-time curvature. Perhaps gravity responds differently to vacuum than to other forms of energy, filtering out most of the vacuum contribution by a mechanism we have not discovered. Perhaps our effective field theory accounting breaks down in curved space-time, and the naive sum of modes is the wrong calculation. Every option implies that nothing is not a passive backdrop. The climax of this chapter is not a solved mystery, and it should not pretend to be one. It is the realization that the universe's expansion is governed by something that looks like emptiness, and that this emptiness has a measurable gravitational signature. The same concept that seemed like a semantic trap becomes a driver of cosmic history, inferred from the dimness of dying stars and the pattern of galaxies across the sky. The paradox shifts from where expansion goes to what the vacuum is, and that shift is the real reveal. Acceleration draws a hard line between existence and observability, and this line is drawn by geometry rather than by walls. There may be regions of the universe that exist but are forever causally disconnected from us. Not only now, but forever, because the event horizon prevents exchange of signals. There may be a much larger cosmos beyond our horizon, shaped by the same physics, yet permanently inaccessible. The boundary is not a wall in space, it is a limit written into spacetime's evolution. So the next step is unavoidable, and it sets up the next chapter's focus. If horizons define what can be seen, we must define what the observable universe means, not as a vague phrase, but as a precise operational concept. We must separate the universe as a whole from the part that can ever exchange signals with us, because those are not the same thing in an accelerating spacetime. We must ask what it could mean to talk about outside, when outside may be operationally undefined, real in a mathematical model, yet unreachable in principle. We end with the central paradox reframed one last time, so the viewer carries the right mental model forward. The universe is not expanding into nothing. It is expanding by changing what space is, and dark energy suggests the vacuum participates in that change, shaping the metric from within. The more the universe accelerates, the more the observable universe becomes a finite island in an ocean of geometry. Chapter 7 enters that island's boundary and asks what cosmic limits do to meaning itself. We reach the place where the universe may have no edge, but our knowledge does. The central question returns in its final form, sharpened by horizons, acceleration, and the limits of measurement. Start with a precise definition of what we mean by the observable universe. It is not the whole cosmos, and it is not a boundary in space. It is a practical region defined by what can, in principle, leave evidence in our instruments, light, neutrinos, and even gravitational waves, all constrained by cosmic time. When we picture it on screen, it looks like a luminous sphere centered on us. That image is useful, yet it hides a deeper truth. Every observer carries their own observable universe, because the boundary is built from their history of received signals. The particle horizon is the maximum distance light could have traveled to us since the hot beginning. It marks what has had time to reach our detectors, given the expansion history. In technical terms, it is set by integrating the speed of light over cosmic time while accounting for the changing scale factor. That detail matters because the universe did not expand at a single steady rate. Radiation domination, matter domination, and dark energy domination each reshape the integral, so the horizon is a record of the entire expansion timeline. Visually, imagine a spacetime diagram with time rising upward and distance spreading sideways. Our past light cone opens like a widening searchlight, and the particle horizon sits where that cone meets the earliest times we can meaningfully describe. The event horizon is different and more unsettling in an accelerating universe. It is the maximum distance from which light emitted now can ever reach us, even with infinite waiting. If acceleration persists, there are events happening today whose future messages are already doomed to remain unheard. These horizons are causal boundaries created by space-time dynamics, not walls made of matter. They arise because the metric can stretch the gap faster than signals can close it. The key is that relativity limits local motion through space, while the geometry that defines distance can evolve globally. Now connect this to the hook about the growing map. Distances can stretch everywhere at once, while information still moves locally at light speed. A galaxy can recede faster than light in terms of proper distance, yet no object outruns a nearby beam of light in its own neighbourhood. When we ask what lies beyond the observable universe, we must keep the meaning operational. Beyond means regions of space-time whose signals have not arrived or will never arrive. It is a statement about causal contact, not about what exists in some absolute sense. Beyond does not mean an exterior void surrounding the universe like air around a balloon. It means parts of the same space-time that are causally disconnected from our world line. The phrase outside tempts the mind toward geography, even though the issue is communication. This is why expansion creates a boundary without creating an edge. The limit is in measurement, inference, and shared history, not in the existence of more space. The universe can be larger than what we see without needing any surrounding container. The temptation is to imagine a frontier where the universe ends and nothing begins. General relativity does not require such a frontier, and most cosmological models avoid it. Historically, this shift was one of the great conceptual turns after Einstein. Space and time became dynamic, not a fixed stage. Consider the simplest geometry first, because it matches current data well. A flat FLRW universe can be spatially infinite, with no center and no boundary. Flat here means Euclidean geometry on large scales, so parallel lines behave as expected and triangles add to 180 degrees. In an infinite flat space, expansion never reaches an edge because there is no edge to reach. The scale factor changes the metric everywhere, and infinity stays infinity. If the cosmos is infinite today, it was infinite yesterday as well, only the distances between co-moving points were smaller. Now consider a closed universe with positive spatial curvature. It can be finite in volume yet unbounded, like the surface of a sphere without an edge. The analogy is imperfect because our space is three-dimensional, but it captures the central idea of being finite without having a border. In that case, travelling far enough in one direction does not meet a wall. It eventually returns, because the geometry closes on itself without needing an outside. The outside of the sphere exists in the embedding picture, but the two-dimensional surface does not require it to be defined. Negative curvature offers another option, often infinite and open. It also has no edge, because the geometry extends without a boundary in its own intrinsic description. In a negatively curved space, geodesics diverge faster, and triangles have angle sums less than 180 degrees. Cosmologists test these possibilities using the cosmic microwave background. The CMB acts like a distant screen at a known redshift, and its acoustic peak pattern constrains curvature by telling us how large standard features appear on the sky. Exotic topologies complicate the picture without restoring a literal border. Space could be multiply connected, like a three-dimensional torus with wraparound identifications. In such a universe, moving far enough in a straight line could bring you back, not because of curvature, but because of global identification. Such topologies can be finite yet edgeless, and they can leave subtle patterns. Repeated structures or matched circles in the CMB would be clues, though none are confirmed. The search is ongoing because the signal is delicate, and cosmic variance limits how much sky can reveal, so the word outside becomes a linguistic trap. In these models, outside is not a place you can point to, because the universe is not an object embedded in a larger room. What we call space is already the set of relationships that define location and distance. Yet the observable universe still feels like a bubble around us, because light has a finite travel time. That bubble is defined by our past light cone, not by cosmic architecture. When we look outward, we also look backward, and the view becomes a layered time capsule. The visuals here are almost cinematic. Nearby galaxies glow in mature spirals, while farther ones blur into younger shapes, and beyond them the CMB appears as a faint uniform afterglow, an image of the universe at roughly 380,000 years old. Now connect horizons to the late-time acceleration from dark energy. Acceleration makes the event horizon finite, so the future contains a permanent limit on contact. The discovery in the late 1990s, using Type Ia supernovae as standardizable candles, forced this horizon back into the story. Over time, more galaxies crossed beyond that event horizon in moving coordinates. They are not destroyed, but their future signals can never reach us. Their light becomes increasingly redshifted, stretched into wavelengths so long that it fades below any practical detectability. This is the same logic that allowed superluminal recession without violating relativity. The metric can increase proper distances faster than c, while local physics remains causal. In a small region, special relativity still governs, and no observer sees nearby matter outrun light. The observable universe is therefore a moving boundary, and it depends on the expansion history. Change the history, and you change what is observable, even in principle. A universe that decelerates forever has a different causal structure than one that accelerates toward a de Sitter-like future. This is where inflation returns, because inflation is a horizon story as much as a beginning story. It solved the horizon problem by stretching a once causal patch beyond our current particle horizon. Regions that look mysteriously uniform today could once have been close enough to equilibrate. Inflation also explains why the universe appears nearly flat. Rapid expansion dilutes curvature, the way a balloon's surface looks flatter as it grows, and the mathematics makes that intuition precise through the evolution of the curvature term in the Friedmann equations. Inflation also suggests that our observable region is a tiny sample of a much larger spacetime. The patch we see could be a small island in a vastly larger inflating background. If so, the smoothness we observe is not a global guarantee, but a local inheritance from an earlier phase. In many inflation models, the inflaton field decays locally and ends inflation in pockets. Those pockets reheat and become hot Big Bang regions, often called bubble universes. Reheating is not just a narrative beat, it is a physical transfer of energy from a field into particles and radiation. If inflation is eternal, the process never ends everywhere at once. Some regions keep inflating while others thermalize, producing a mosaic of bubbles separated by inflating space. Quantum fluctuations can keep parts of the inflaton field high on its potential, sustaining expansion in those domains. Different bubbles could settle into different vacuum states, with different low-energy physics. The multiverse idea enters here as a consequence of certain potentials and quantum fluctuations. In some frameworks, even the effective values of constants could differ, depending on how symmetry breaking unfolds after reheating. We must separate what is theoretical from what is observed, because the word multiverse can outrun the evidence. Inflation is strongly motivated by CMB statistics, but eternal inflation is not directly confirmed. The data point toward an early accelerated phase, yet they do not uniquely select the deepest version of the idea. Bubble collisions could leave signatures, like anisotropic scars or unusual correlations in the CMB. Searches exist, but no decisive detection has survived scrutiny. The challenge is that many foregrounds and statistical flukes can mimic the patterns, and the sky gives us only one realization to analyze. Even without collisions, inflationary models can be constrained by what we do see. The spectral tilt, Gaussianity limits, and tensor bounds narrow the space of viable potentials. Each constraint is a different window into the inflaton's dynamics, because the shape of the potential controls how fluctuations are generated. Large-scale structure adds another set of constraints, because it tracks how primordial fluctuations grew. The distribution of galaxies tests the same initial conditions that the CMB encodes. Baryon acoustic oscillations, in particular, preserve a standard ruler whose imprint links early universe physics to late-time expansion. This is where humility becomes a scientific method rather than a mood. Cosmology advances by asking what counts as evidence when experiments are impossible and only one universe is available. The discipline is to treat the sky as a laboratory while admitting that some knobs cannot be turned. A model earns trust when it predicts multiple independent observables with one parameter set. It loses trust when it can fit anything by adding untestable freedom. That balance between explanatory reach and empirical restraint is what keeps speculation from becoming mythology. The Hubble tension remains a live example of that discipline. If the tension is real, it could point to new physics that changes early expansion or late-time inference. It may involve subtle systematics, or it may hint at extra energy components, modified recombination, or other shifts that alter the inferred distance ladder. But even a resolved tension would not give us access beyond the horizons. Better measurements refine the map, yet they cannot turn a causal boundary into a doorway. The limit is not merely technological, it is written into the causal structure of space-time. So what does it mean to talk about the universe outside the observable region? It means extending a model beyond the data, guided by symmetry, simplicity, and consistency with known physics. We do this cautiously, because the extension is an extrapolation, not a direct observation. This is not meaningless, but it is conditional. The claims are only as strong as the assumptions that carry them beyond what can be observed. The question becomes, which assumptions are minimal, and which are conveniences that could fail in regimes we cannot test? Now return to the phrase expanding into nothing, because this is the documentary's core paradox. The phrase sneaks in a container model that general relativity does not use. It imagines space as a substance that must occupy a pre-existing emptiness, as if the universe were a gas filling a box. In general relativity, cosmic expansion is the time evolution of the spacetime metric in an FLRW solution. The scale factor changes the conversion between coordinate separation and proper distance. This is why a grid drawn on space can stretch smoothly, with galaxies roughly at rest in comoving coordinates. Nothing external must be supplied for that change to occur. The geometry is not sitting inside a larger emptiness, because the geometry is the arena in which emptiness is defined. Asking what space expands into is like asking what time flows through, an intuitive question that misfires on the formal structure. When people insist on an outside, they are asking for an embedding space that the equations do not require. An embedding can be drawn for intuition, but it adds structure not demanded by observations. The balloon picture is a teaching tool, yet it can quietly smuggle in an extra dimension that the physics never mentions. So the clean conceptual answer is this. The universe does not expand into an external nothing, because there is no external space in the model. Expansion is internal to spacetime, a change in the metric relations that define distance, volume, and the propagation of light. What about nothing inside the universe, the vacuum that seems to drive inflation and dark energy? That nothing is not absence, but a physical state with energy density and pressure. In the stress energy tensor, vacuum energy behaves like a component with negative pressure, which in turn drives accelerated expansion. In quantum field theory, the vacuum has structure and fluctuations. In gravity, that structure can act like a cosmological constant, or like a field with negative pressure. Even empty space can polarize, fluctuate, and store energy, and those properties can have real gravitational consequences. So the word nothing splits into two meanings that must not be mixed. There is no need for an exterior void, and the interior vacuum is not truly empty. One nothing is a mistaken container, while the other is a subtle physical state that can shape the universe's fate. This resolves the paradox by changing the grammar, not by dodging the physics. Expansion is not a substance spilling outward, but a rule for distance changing with time. The map grows because the metric evolves, and the growth is everywhere at once, not at a frontier. The remaining discomfort is real, and it belongs to the limits of our theories. We still do not know why the vacuum energy is so small, or why it nearly cancels. The mismatch between naive quantum estimates and observed dark energy is one of the most persistent clues that our understanding is incomplete. We also do not know whether inflation was eternal, or what quantum gravity replaces near the earliest times. The map ends where testability ends, and that boundary is not shameful. It is a reminder that science is a method for the reachable, even when it dreams about the unreachable. Yet the core picture is stable across these unknowns. Horizons define what can be seen, geometry defines what can expand, and outside is not a required concept. The universe may be far larger than our light can ever survey, but the rules that shape our survey are well understood. Close by, returning to the hook one last time. The map grows because the scale changes everywhere, not because new territory is added at the edge. If the camera pulls back from our galaxy to the cosmic web, the web itself stretches. Filaments lengthen, voids widen, and the pattern remains coherent. Space is the room, not an object in the room. When the room itself can stretch, asking what it stretches into becomes the wrong kind of question. A better question is what the stretching does to horizons, to energy densities, and to the long-term visibility of the cosmos. Beyond the observable, there may be more galaxies, more history, and perhaps other bubbles with other vacua. But beyond is still within spacetime, not beyond it. The unseen is not a separate realm. It is simply the part of the same reality that cannot yet or cannot ever send us a message. The paradox dissolves when we stop picturing the universe as a thing surrounded by nothing. The universe expands by changing what space is, and our horizons mark the limits of knowing. And in that limit, half scientific boundary, half philosophical mirror, we see what the universe reveals about us. Across this journey, the paradox of expanding into nothing slowly dissolved. Not because we found an outside, but because we corrected the metaphor. Redshift became our receipt, the CMB our fossil light, and the distance ladder our measuring tape, all pointing to a universe whose separations grow in a precise law-like way. In general relativity, that growth is not galaxies rushing through a pre-built void. It is the metric itself evolving, turning space from a passive backdrop into a dynamical participant. Inflation then showed how the universe could become smooth, flat, and seeded with structure by stretching a once causal patch beyond what any signal can now stitch together. Quantum theory complicated the word nothing, revealing a vacuum with structure, fluctuations, and energy, while dark energy showed that the expansion is not merely continuing, it is accelerating and shaping what will remain observable. And at every step, horizons replaced edges, reminding us that beyond often means causally disconnected, not physically outside. Yet the deepest thread stayed taut. The Hubble tension hints that our expansion history may still be missing a chapter, and the cosmological constant problem insists that our bookkeeping between quantum fields and gravity is profoundly incomplete. When we run the equations backward and the fabric frays into geodesic incompleteness, we meet the limit of smooth spacetime itself, and the open question of what replaces it at the beginning. So the story ends where good science often ends, with a clearer map of what we know and sharper outlines around what we do not. What then does it mean for the universe to expand with nowhere to go, if there is no external container and no edge to cross? It means expansion is not motion into an emptiness. It is the changing of distances that define space, a growth of geometry from within. The question, what is it expanding into, is partly a category error, but it also points to a real mystery, because asking about an outside is really asking what spacetime is made of, and whether nothing is vacuum, geometry, or the absence of both. If there is a final twist to the space paradox, it is that the universe does not need room to grow, because room is what the universe is. And when we listen closely through redshift, relic light, and the quiet push of dark energy, we find that nothing is not an answer waiting beyond the cosmos, but a frontier inside our theories, where space, time, and vacuum still refuse to agree. If you want to follow that frontier, keep watching the next measurements, the next surveys, and the next cracks in the model, because the expansion history is also a test of reality's deepest rules. What then does it mean for the universe to expand with nowhere to go, if there is no external container and no edge to cross? It means expansion is not motion into an emptiness. It is the changing of distances that define space, a growth of geometry from within. The question, what is it expanding into, is partly a category error, but it also points to a real mystery, because asking about an outside is really asking what spacetime is made of, and whether nothing is vacuum, geometry, or the absence of both. If there is a final twist to the space paradox, it is that the universe does not need room to grow, because room is what the universe is. And when we listen closely through redshift, relic light, and the quiet push of dark energy, we find that nothing is not an answer waiting beyond the cosmos, but a frontier inside our theories, where space, time, and vacuum still refuse to agree. If you want to follow that frontier, keep watching the next measurements, the next surveys, and the next cracks in the model, because the expansion history is also a test of reality's deepest rules.